Welcome to the Deep Dive. Today we are taking on a source document so foundational and technically dense that we've instituted a new protocol for its analysis, the unabridged protocol. We're going to go slow, we're going to go deep, and we are going to explain, well, pretty much every single sentence and formula that drives the physics.
Indeed. We are diving into really a monumental work from the field of dynamical systems, specifically looking at the emergence of collective order in coupled phase oscillators. Our source is amplitude expansions for instabilities in populations of globally coupled oscillators. Right. And our mission, simply put, is to understand the precise mathematical mechanism, the bifurcation that causes a massive population of, chaotic, disordered elements to spontaneously synchronize. It's fascinating stuff.
It really is. This seminal work, dated October 28, 1993, was penned by John David Crawford from the Department of Physics and Astronomy at the University of Pittsburgh. It's a deep dive that requires us to get our heads around tools like bifurcation theory and center manifold reduction. So let's just jump right in, starting immediately, moving sentence by sentence through the abstract. #, processing the abstract. Linear progression and granularity.
Okay, sentence 1. It lays out the intellectual roadmap. We analyze the nonlinear dynamics near the incoherent state in a mean field model of coupled oscillators.
All right, let's start unpacking the phrase nonlinear dynamics. Why is that word nonlinear so crucial when we talk about synchronization? It sounds basic, but it's fundamental.
It absolutely is, because if the system were linear, the response would just be directly proportional to the input. Synchronization, however, is an emergent phenomenon. The whole is, greater than the sum of its parts.
Right, things don't just add up simply.
Exactly. You need nonlinearity to describe those complex interactions where maybe small changes in the system parameters can lead to massive qualitative changes in behavior. Without nonlinearity, you never achieve collective order. You'd only get independent, sort of dull responses.
Okay, got it. And the mean field model. That sounds like a simplification for a massive population problem. How does that work, practically speaking?
Well, imagine you have a billion fireflies, right? Trying to track every single firefly interacting with, 999 million others is completely intractable.
Impossible.
Totally. So the mean field approximation says, let's assume each firefly only interacts with the average brightness that's the field of the entire swarm. This statistical trick, averaging the influence of the whole population, allows us to replace those impossible nodal body dynamics with a single solvable statistical physics problem.
Makes sense. So that sets up our goal. We are observing the behavior as the system transitions away from the incoherent state. That's the starting point of total chaos, right? Where all the oscillator phases are randomly distributed, resulting in zero net macroscopic order.
Precisely. We're analyzing the moment that chaotic equilibrium becomes unstable. So let's proceed to the methodology, the how.
Okay, sentence number 2. This defines the core mathematical framework. The population is described by a Fokker-Planck equation for the distribution of phases, and we apply center manifold reduction to obtain the amplitude equations for steady state and Hopf bifurcation from the equilibrium state with a uniform phase distribution.
Whoa, okay, lots to unpack there.
Yeah, we definitely need to pause here for 2 critical foundational concepts, the Fokker-Planck equation and the center manifold reduction. First up, why is the Fokker-Planck equation a partial differential equation, the right tool for describing this population? Why not track individuals?
Right. Because we're dealing with a huge population, essentially infinite in the continuum limit, we stop tracking individual phases, just not feasible. Instead, we track the density of phases. The Fokker-Planck equation describes the time evolution of this probability density function.
So it's statistical.
Exactly.
Yeah.
This PDE elegantly combines 2 essential forces: the deterministic drift, that's the interaction and natural frequency rotation, and the random diffusion, which is the effect of noise, represented by dollars. Fundamentally, it's a statement of mass conservation. The number of oscillators has to be conserved, but with this added diffusion term.
Okay, that covers Fokker-Planck. Now, for the technique that makes the problem actually solvable, center manifold reduction. The Fokker-Planck equation describes an infinite dimensional system. That sounds terrifying. How does the center manifold theorem tame that complexity?
Yeah, infinite dimensions are usually bad news for calculations, but this is the mathematical powerhouse. When this infinite dimensional system gets pushed past the point of stability, the bifurcation point, it turns out that only a finite number of modes, the so-called critical modes, actually become unstable.
Ah, so most directions are still stable.
Precisely. The rest of the modes are quickly damped out, they decay away. The center manifold theorem provides the rigorous mathematical framework to project the infinite dimensional dynamics onto just that handful of critical slow modes. So we replace the monstrous PDE with a simple set of finite dimensional amplitude equations, much easier to handle.
And those amplitude equations then predict the types of instability we might see: steady state and Hopf bifurcation. Can you quickly define those?
Sure. A steady state bifurcation is the simplest type. A new time-independent synchronized equilibrium state emerges. The net macroscopic order parameter, which we'll call it then dollars, becomes constant and positive. Basically, the system settles into a stable synchrony. A Hopf bifurcation is more exciting, dynamically speaking. The loss of stability leads to a new time-periodic solution. So instead of settling down, you get a sustained macroscopic oscillation, resulting in rhythmic collective behavior. Think synchronized flashing or pulsing.
Okay, I think that covers the second sentence of the abstract then. We've defined the mathematical pipeline, starting with the statistical density via Fokker-Planck, simplifying it down to the core dynamics using center manifold reduction. And that results in predictable instabilities, the bifurcations. Have we missed any nuances regarding the definition of the equilibrium state itself?
Good check. I think we've established that the uniform phase distribution mentioned is mathematically identical to the incoherent state we talked about earlier, where the order parameter $3 is 0 and the system is essentially at rest, completely disordered. Yeah, I think we're good. Let's look at the crucial element of symmetry next.
All right, sentence 3. When the population is described by a native frequency distribution that is reflection symmetric about 0, the problem has circular symmetry. Symmetry always seems important in physics.
Oh, absolutely. Symmetry is basically the physics telling the mathematics what kinds of solutions are even possible. Reflection symmetric about 0 means the distribution of natural frequencies, which we call g omega of omega, is an even function. So mathematically, g omega omega equals g of minus omega, meaning for every oscillator that naturally wants to spin clockwise at a certain speed, there's a mirror image counterpart that wants to spin counterclockwise at that same speed. Perfect balance.
And this perfect balance confers the circular symmetry. What does that mean mathematically?
Yes. Formally, this is O2 symmetry. It combines rotational invariance, you can spin the whole system, and the physics doesn't change in reflection invariance. The mirror image physics is also valid. This symmetry is absolutely critical because, as we'll see later, it forces the key eigenvalues, the things that determine stability, to be degenerate.
Degenerate meaning they come in pairs.
Exactly. They exist in pairs or sometimes even larger groups. And ignoring that degeneracy, as we'll find out, leads to fundamentally incorrect stability predictions. It's a major point of this paper.
Okay, very important. Let's move to sentence 4, which presents one of the paper's core intellectual contrasts. In the limit of 0 extrinsic noise, although the critical eigenvalues are embedded in the continuous spectrum, the nonlinear coefficients in the amplitude equation remain finite, in contrast to the singular behavior found in similar instabilities described by the Vlasov-Poisson equation.
Right, this is fascinating. Here's where the Kuramoto model, or rather the Fokker-Planck description of it, proves robust in a way other similar kinetic systems do not.
So what's the historical issue with the Vlasov-Poisson equation? You often see that used in plasma physics or gravity systems, right?
Yes, exactly. In those systems, which are typically collisionless, the main damping mechanism is often something called Landau damping. When researchers tried to apply bifurcation theory to Vlasov instabilities, they often ran into a mathematical nightmare. As you try to remove the damping mathematically, as the parameter analogous to noise, let's call it $, approaches 0, the nonlinear coefficients that predict the stability of the new state often diverge. They might blow up like proportional to $, to the -3.
Which makes the prediction useless at 0 noise.
Worse than useless. It makes any prediction about the 0 noise limit potentially nonsensical or suggests the system is inherently unstable in that limit. It makes the theory very fragile.
So the Vlasov system stability predictions kind of fall apart without noise, but the Kuramoto-Fokker-Planck system's predictions hold up. That's the claim here.
That's exactly the claim. Crawford's finding that the nonlinear coefficients for the system remain finite as $0 goes to 0 is huge. It means that the predicted stable synchronization states are physically robust. They persist even in the theoretical limit of a perfectly noiseless environment. This is a crucial mathematical distinction between these two major classes of infinite dimensional dynamical systems.
Okay, that definitely covers the fourth sentence. We get the Vlasov-Poisson contrast. the confirmation of the robust finite nature of the nonlinear coefficients in the zero noise limit. Have we missed any nuances regarding the emergence of eigenvalues from the continuous spectrum that was mentioned briefly?
Yeah, good point. We've basically established that the eigenvalues, the discrete modes driving the instability, emerge from this background sea of damped continuous modes. But once they emerge, they form a discrete controlling set. The robustness, the finiteness is the key message, though. Let's examine the specific case that yields the most complex behavior discussed in the abstract.
Okay, sentence 5. For a bimodal reflection-symmetric distribution, both types of bifurcation are possible, and they coincide at a codimension 2 Takens-Bogdanov point.
Right, so bimodal. That means the frequency distribution omega has two separate peaks. Think of a population made up of two distinct subgroups. Maybe one group naturally oscillates fast, the other naturally slow, but they're all interacting together. This structure allows for a much richer interplay between symbol synchronization and collective oscillation.
And the result of this richer structure is the possibility of hitting this codimension 2 Takens-Bogdanov point.
Yeah.
Okay, we need a simple analogy for this kind of high codimension critical state. It sounds complicated.
It is complicated, but think of it like this. Imagine a master control panel for the system's stability. Usually you turn one knob, say the coupling strength dollars, and maybe the system goes unstable in one specific way, like settling into a steady state bifurcation, or maybe turning that knob makes it start oscillating, Hopf bifurcation. The Takens-Bogdanov point is special. It's like a point on that control panel where two different types of catastrophe, the steady state failure and the periodic failure, happen at the exact same moment. Codimension 2 means you need two control knobs or parameters to tune the system precisely to that critical merger point.
So like the coupling strength dollar might be one knob.
Right, and maybe the distance between the two frequency peaks, let's call it omega naught, is the second knob. Only when both are tuned perfectly does the steady state bifurcation, where a real eigenvalue crosses the imaginary axis, merge exactly with the Hopf bifurcation, where a complex conjugate pair of eigenvalues crosses.
So the Takens-Bogdanov point is like the mathematical crossroads where the system decides whether to settle into a steady synchronized state or break into perpetual rhythmic oscillation.
That's a great way to put it. It's the highest point of degeneracy covered in the paper, and it signals extremely complex dynamics nearby. It's a really interesting spot mathematically.
Okay, now sentences 6 and 7 describe the outcomes of these bifurcations. The steady-state bifurcation may be supercritical or subcritical and produces a time-independent synchronized state. The Hopf bifurcation produces both supercritical stable standing waves and supercritical unstable traveling waves.
Right, so when we say supercritical versus subcritical, we're describing let's say, the softness or hardness of the transition. Supercritical means the new state, the synchronized state, or the wave emerges gradually as you increase the control parameter, like K, and it's stable right away.
Like a smooth onset.
Exactly. Subcritical is different. The new state might actually appear below the critical point, but it's unstable initially. This often leads to hard transitions, maybe with hysteresis, where you might need a large initial disturbance to kick the system into the synchronized state. And once it's there, it might persist even if you lower K back down a bit.
Okay, and now the crucial stability results for the Hopf bifurcation, the oscillating states.
Yes, this is key to the paper's contribution. The periodic output, the oscillation, comes in two flavors according to this analysis. Standing waves, SW, which Crawford shows are stable, and traveling waves, TW, which he shows are unstable.
Can you give a quick physical picture? Standing versus traveling?
Sure. Physically, standing waves are like two distinct synchronized clumps of oscillators, oscillating sort of out of phase, but remaining fixed in their average position in phase space. They breathe in synchrony. Traveling waves are more like a single synchronized clump that circulates continuously around the phase circle.
Okay, and that distinction, stable SW, unstable TW, sets the stage for the paper's primary correction, which comes in the final sentences of the abstract. Previous work on the Hopf bifurcation in a bimodal population by Bonilla, and Spigler, and Okuda and Kuramoto predicted stable traveling waves and stable standing waves, respectively. A comparison to these previous calculations shows that the prediction of stable traveling waves results from a failure to include all unstable modes.
Boom, there it is.
So, the stability prediction for the traveling wave by Bonilla, and Spigler was wrong. And the entire reason it was wrong goes back to ignoring the O2 symmetry we discussed just a minute ago. Is that right?
That's the entire intellectual cornerstone of Crawford's work here. O2 symmetry mandates that the complex eigenvalue associated with the Hopf bifurcation must have a multiplicity of 2, meaning 2 linearly independent eigenvectors span that unstable space. Bonilla and colleagues essentially neglected the second reflected eigenvector, which we can call kappa dot psi kappa dot psi.
They only considered one direction of instability.
Effectively, yes. By failing to include the full spectrum of unstable modes required by the symmetry in their center manifold reduction, their simplified amplitude equations only predicted the traveling wave solution. And crucially, they incorrectly found it to be stable.
Wow. So ignoring the mirror image literally gave them the wrong physics.
It fundamentally did. Crawford's work proves that when you correctly include the O2 constraint, the resulting amplitude equations reveal 2 coexisting solutions, the stable standing waves and the unstable traveling waves, thereby resolving the significant discrepancy in the literature at the time.
Okay, and the abstract finishes with source content, keywords, oscillators, bifurcation, symmetry. That seems to wrap it up nicely. We finished the abstract, setting up the model, the framework, the critical Vlasov contrast, the Takes-Bogdanov point, and this crucial stability correction based on O2 symmetry. Have we missed any critical rhetorical purpose of the abstract itself before we move on?
I think we've thoroughly unpacked it. The abstract functions as a really comprehensive summary, doesn't it? It sets up the key results and intellectual contributions, particularly highlighting that correction of prior work, which is often a major goal of scientific papers. Yeah, let's proceed to the paper's contents and the introduction.
Okay, section 1, the introduction. Paragraph 1.1 kicks off by discussing the history, mentioning pioneers like Winfrey and Kuramoto, and introduces the canonical Kuramoto model for phase dynamics. We need to look closely at equation 1, the master equation for the individual oscillator dynamics. It reads, Theta sub I plus theta dot sub I equals omega sub I plus k over n times the sum from j equals 1 to n of sine of theta sub j minus theta sub I plus cs sub I of t.
Yeah, this is the equation that really launched 1,000 synchronization studies. Building on Winfrey's earlier insights, it perfectly captures the essential dynamics, doesn't it? You have the oscillator's natural tendency to rotate at its own frequency, omega ta omega sub I.
Right, its internal clock.
Exactly.
Yeah.
And that's counteracted, or rather influenced, by the collective synchronization force, which is that summation term. The interaction is mediated by the sign of the phase difference between oscillator dollars and oscillator dollars.
And the sign function in that summation term is really crucial, isn't it? How does that specific function drive synchronization?
It's perfectly suited for it. The sign function ensures that oscillators tend to pull each other toward alignment. If 2 oscillators are exactly in phase, the sign is 0, no interaction. If they're 180 degrees out of phase, the sign of pi is also 0, so they effectively ignore each other in this simple model.
Yeah.
But if one is slightly ahead of another, the sign function creates a pull to slow the leader down and speed the laggard up, pulling them towards each other.
And the strength of that pull is set by tall dollar.
Precisely. Tau dollars is the coupling strength, determining how strongly each oscillator feels the influence of the collective. And notice it's divided by $9, the total number of oscillators. This scaling ensures the total coupling effect doesn't just blow up as the system size increases. Finally, there's the Te sub I of T term, which represents noise, added later by Sakaguchi, I believe.
Okay, that covers the first equation. Have we missed any nuances there?
I think we've nailed down the components. Natural frequency, coupling interaction via sign of phase difference, coupling strength K, and scaling, and the noise term. Let's move to the next paragraph.
Paragraph 1.2 introduces the macroscopic measure of synchrony, the order parameter, defined in equation 2. Sum Tm, sum share of t times e to the ipi of t equals 1 over n times the sum from j equals 1 to n of e to the I theta sub j of t.
Right, this is the macroscopic variable we actually care about when talking about collective behavior. $3 of t, the magnitude, measures the coherence or the degree of synchronization. It ranges from 0 for complete incoherence, chaos, up to 1 for perfect phase alignment.
And a t is the average phase of the population, telling you the collective position on the phase circle, if you like. The incoherent state corresponds to Procus dollars. Synchronization emerges when torque dollars become significantly greater than 0.
Okay, clear definition of the order parameter. Have we fully grasped its role?
Yes, it's our main diagnostic tool for seeing synchronization happen. On to Kuramoto's famous result. Paragraph 1.2 also mentions Kuramoto's original result for the critical coupling needed to see synchronization begin, but specifically in the absence of noise, $2 dollars, that's equation 3. AEOC equals 2 over pi times g of 0.
Yeah, this is a beautiful analytic result. It elegantly links the microscopic interaction strength, the dollars required for instability, K sub c, to the statistical properties of the population itself, specifically g dollars of 0, which is the density of oscillators right at the mean frequency, assuming a symmetric distribution centered at 0.
So the diversity matters. If GD is low, few oscillators near the average speed, you need stronger coupling dollars to synchronize them.
Exactly. If the population is very diverse, low G dollar, it's harder to pull them together. If they're very similar, high G dollars, synchronization happens more easily at lower dollars. This equation defines the threshold for synchronization onset in the simplest case.
Okay, we've covered the definition of KC dollars in the noiseless case. Are you ready for the next step?
Yep, we've set up the basics. Individual oscillators, order parameter, and the basic threshold. Now the introduction moves towards the continuum limit.
Right. Paragraph 1.3 notes the subtlety of stability, even for the incoherent state, and introduces the need for the Fokker-Planck equation, equation 4, following work by Sakaguchi, to handle the large Nadia limit. We looked at this equation in the abstract, but let's re-examine it. Frac partial flutter plus the partial derivative of rho with respect to t plus the partial derivative of rho times v with respect to theta equals d times the second partial derivative of rho with respect to theta squared.
We identified the terms before. Time evolution of the density dollar, the drift term involving the velocity dollar, and the diffusion term involving d-lar. Paragraph 1.4 defines other more carefully.
It says rho, theta d omega times g of omega times rho of omega galar times rho of theta omega dd. T dou omega describes the number of oscillators in specific phase and frequency bands, and equation 5 gives the normalization.
Equation 5 is d theta omega t RL and 2. The integral from 0 to 2 pi of d theta rho of theta omega t equals 1. This just says that for any given natural frequency omega, if you sum up the density matter over all possible phases to theta from Bala to 2 pi, you have to account for 100% of the oscillators at that frequency. They have to be somewhere.
Standard probability normalization. Okay. Have we fully defined the Fokker-Planck equation and the density rho?
I think so. We have the equation governing the density evolution and the meaning of the density itself, plus its normalization. Let's see how the velocity and order parameter translate.
Paragraphs 1.5 and 1.6 show how the microscopic phase velocity from equation 1 and the order parameter from equation 2 are re-expressed using this continuous density rho. Let's look at the velocity, equation 7. Follow data omega plus k omega plus k s theta omega t equals omega plus k RT sine of psi minus theta.
Right, so this is just the velocity term from the original Kuramoto equation, but now the collective influence isn't a sum over n oscillators. It's expressed directly in terms of the macroscopic order parameters at PST, which themselves depend on the density one.
And the order parameter itself in the continuum limit, equation 8, greater than e theta, d de omega, g I theta, d theta is in the times e to the I ti of t equals the integral from 0 to 2p of d theta times the integral from minus infinity to infinity of d omega of rho of theta omega t times g of omega times e to the I theta.
Yep, this is the direct continuum analog of equation 2. Instead of summing e to the I theta sub j over all local oscillators, we're integrating e to the I theta weighted by the density of theta, omega t, and the frequency distribution g omega of m over all frequencies and phases. It's the same concept, just translated into integral form.
Okay, we've successfully translated the core microscopic concepts, velocity, order, parameter, into the continuum framework using the density rock. Are we comfortable with these continuum forms?
Yeah, they're the standard definitions in this field. Makes sense. Now let's look at the noise definition again.
Paragraph 1.7 connects back to the noise z I sub I of t from equation 1, defining its statistical properties, which ultimately determine the diffusion coefficient dollars in the Fokker-Planck equation. 4. Equation 10 is the key statistical definition. The expectation value of c sub I of s times c sub y of t equals 2d times delta sub I times delta of s minus t.
Right, let's break this down because it's important. The angle brackets wangle mean average or expectation value. The term c sub I of s times c sub j of t is the correlation between the noise felt by oscillator dollars at time and oscillator d dollars at time.
And the right side tells us about that correlation.
Exactly. The first delta sub ij, is the Kronecker delta. It's 1 if null is and dollars if $1. This means the noise is uncorrelated between different oscillators. What happens to oscillator dollar is independent of what happens to oscillator dollar.
Okay, reasonable assumption for simple noise.
The second delta of s minus t, is the Dirac delta function. It's essentially infinite if s and 0 otherwise. This means the noise is instantaneous in time. It's uncorrelated with itself at any two different times. This is the definition of white noise.
And the $2 factor.
That $2 term is critical. It explicitly connects the strength of the microscopic noise fluctuations, defined by this correlation function, to the macroscopic diffusion coefficient dollars that appears in the Fokker-Planck equation. This equation provides the bridge between the micro and macro descriptions of noise.
Got it. So we've fully defined the noise characteristics and linked them to the diffusion term.
Yeah.
We've covered all aspects of equation 10.
Yes, the uncorrelated nature in space between oscillators and time, white noise, and the amplitude connection via $2, we're good.
All right, paragraphs 1.8 and 1.9 introduce the standard procedure for stability analysis, linearization. We look at small deviations, atellities from the uniform, incoherent distribution not a pi naught equals 1 over 2 pi. The Fokker-Planck equation is then rewritten for this deviation that delay. Equation 11 shows the general form. Fokker-Planck atella, the partial derivative of eta with respect to t, equals ln plus n of eta.
Right. This splits the dynamics of the deviation into a linear part, governed by the operator dollars, and a nonlinear part, none dollars of eta, which contains terms that are quadratic, cubic, and higher order in eta.
Equation 12 gives the explicit form of the linear operator didea. It looks pretty complicated. Lida equiv d torre theta for omega theta plus fractated d theta plus phi d eta plus ccu omega, defined as d times the second partial derivative of eta with respect to theta squared minus omega times the partial derivative of eta with respect to theta plus k rho naught over 2 times the quantity e to the minus I theta times the integral of d theta prime and d omega prime of eta ge to the I theta prime plus complex conjugate.
Okay, let's break down Lida Tarot into its physical components rather than reading it all again. There are three main parts.
First part looks like diffusion. Dito partial theta 2d partial squared eta by partial theta squared.
Correct. That term tends to smooth out any bumps in the distribution, driving it back towards uniformity. It's a stabilizing influence.
Second part. Omega partial theta minus omega partial eta by partial theta. That looks like rotation.
It is. That term just describes how oscillators at frequency omega rotate around the phase circle. It doesn't create or destroy synchrony by itself, just shuffles things around.
And the third part, the integral term.
Yes.
That's the coupling, right?
Yes, that's the linearized effect of the mean field coupling term from the original Kuramoto equation. Notice it depends on an integral of dito weighted by dito over all frequencies and phases. This integral term is essentially proportional to the complex order parameter calculated from the deviation data. This is the term that can drive instability if data is large enough. And CC means complex conjugate.
And equation 13 defines the nonlinear term number $1. It's not written out explicitly here, but the text says it depends quadratically on dito and its derivatives. Why is this important later?
Because NOSAR contains the higher order interactions. While the linear operator tells us when the incoherent state becomes unstable, the bifurcation point, the nonlinear term tells us what happens after the instability. Specifically, the lowest order terms in the longit, the quadratic ones, will be used to calculate the cubic coefficients in the amplitude equations, which determine the stability of the newly emerging synchronized state.
Okay, let's pause. We have introduced the full continuum equation for the deviation, broken it down into its linear logger and nonlinear log parts. Have we grasped the why of this structure? Why separate L and N?
Yes, absolutely. The structure partial eta plus n is the standard starting point for bifurcation analysis. The linear part dictates the onset of instability, its eigenvalues crossing the imaginary axis. The nonlinear part nuller dictates the nature and stability of the solutions that emerge after the instability. This separation is crucial for the whole analysis. We are now ready to tackle symmetry again.
Okay, paragraph 1.10 discusses the crucial O2 symmetry again. It arises if the frequency distribution omega is reflection symmetric, equation 18. The symmetry group O2 is generated by rotations, equation 15, and reflections, equation 16. Let's look at those transformations.
Rotation is simple. Equation 15, theta plus phi dot theta omega equals theta plus phi omega. It just means shifting all phases theta by some angle phi. It doesn't change the underlying physics if the system is rotationally invariant.
But reflection is more involved. Equation 16, theta omega equals minus theta minus omega.
Right. This reflection operation kappa kappa simultaneously reverses the sign of the phase eta and the sign of the natural frequency omega, so it maps an oscillator rotating, say, clockwise at speed omega to one rotating counterclockwise at the same speed. The system has this reflection symmetry only if the frequency distribution ega is itself symmetric.
which is equation 18, g omega gauss of omega equals g of minus omega. This is the mathematical condition for the full O2 symmetry to hold.
Precisely. And as we keep saying, this O2 symmetry is not just a mathematical curiosity. It has profound consequences for the structure of the eigenvalues and the resulting dynamics, especially near the Hopf bifurcation.
Okay, we've nailed down the generators of O2 and the condition g omega required for it. Is the significance clear?
Crystal clear. O2 is the key constraint. Let's see what happens if it's slightly broken.
Paragraphs 1.11 and 1.12 explain that even if the mean frequency isn't zero, you can shift to a rotating frame, equation 19, to recover the g omega condition. But if the distribution itself isn't reflection symmetric, the symmetry reduces from O2 rotations and reflections to just SO2 rotations only.
Right. Losing the reflection symmetry breaks the degeneracy that O2 imposes. We'll see later how this perturbation changes the bifurcation structure.
Okay, paragraph 1.13 summarizes the linear stability analysis work by Strogatz and Marollo. They analyzed the spectrum of the linear operator. What did they find?
They found that dollar has a continuous spectrum, basically, a whole block of eigenvalues lying on the vertical line text real lambda, texterney. Real part of lambda equals minus d in the complex plane. These correspond to damped modes. For coupling dollar below the critical value takes ball, all eigenvalues are in the stable left half plane, texture D. The system is stable partly due to phase mixing, which is analogous to Landau damping in plasmas.
But what happens when dollar exceeds texture?
When dicastry lambda, a discrete eigenvalue lambda emerges from this continuous spectrum, specifically from the point lambda diagonus D, and moves into the unstable right half plane. This signals the instability of the incoherent state and the onset of synchronization.
And this critical coupling case here is in the presence of noise dollars is given by equation 21. Chasey fraction d2 plus omega 21 k sub c equals the inverse of the integral from minus infinity to infinity of dg of omega d omega over d squared plus omega squared.
Yes, this is the generalized formula for the critical coupling threshold when noise dollars is present. It was derived by Sakaguchi. Crucially, Crawford notes that it correctly reduces back to Kuramoto's original result, ADC equals 2 over PCO 0, in the limit as the noise dollar goes to 0.
Okay, so we have the linear stability picture, a continuous spectrum plus potential discrete eigenvalues that cause instability when KCCC. Is this picture complete for the linear part?
Yes, that summarizes the findings of Strogatz and Marollo and gives us the formula for KCR of noise. Now, the paper discusses previous nonlinear work.
Right. Paragraphs 1.14 and 1.15 discuss the previous work that this paper aims to correct or clarify. It mentions Bonilla et al. Looked at bimodal distributions and found a Hopf bifurcation, but, as foreshadowed, failed to include both unstable eigenvectors mandated by the O2 degeneracy.
Exactly. They essentially missed half of the critical dynamics because they didn't fully account for the reflection symmetry.
It also mentions Okuda and Kuramoto, who looked at a related model, two distinct subpopulations, which is a special case of Crawford's general Fokker-Planck equation. They did find both traveling and standing wave solutions, consistent with Crawford's later findings.
Yes, but apparently they didn't explicitly connect their findings to the underlying O2 symmetry or perform the rigorous center manifold reduction in the same way. Crawford's work provides the unifying theoretical framework using O2 bifurcation theory.
Okay, paragraph 1.6 outlines the structure of the rest of Crawford's paper. Section 2 will clarify the spectrum of dollars dealing with complex eigenvalues, non-semi-simple eigenvalues, at the Takens-Bogdanov point. Section 3 will derive the amplitude equations using center manifold reduction,
setting the agenda for the detailed calculations to come.
And paragraph 1.76 hammers home the key points again. The crucial contrast with Vlasov instabilities, coefficients remaining finite as 0 to 7. The explicit use of the well-established theory of bifurcation in systems with O2 symmetry, and it previews the main result for the bimodal population again. The Hopf bifurcation yields supercritical stable standing waves, SW, and supercritical unstable traveling waves, TW.
Re-emphasizing the central contributions before diving into the math.
Okay, we've finished the introduction. We've set up the Kuramoto model, moved to the Fokker-Planck framework, defined the order parameter, discussed the crucial O2 symmetry constraints, summarized the linear stability results, including the critical coupling $2n, and clearly stated the paper's mission to correct prior work using rigorous O2 theory, particularly regarding the Hopf bifurcation stability. Have we missed any critical details or context before diving into the spectrum analysis in Section 2? No, I think we've thoroughly unpacked it. We understand the physical model, the mathematical framework, Fokker-Planck, linearization, the importance of symmetry, the basic stability picture, and the specific discrepancy in the literature that this paper addresses. We have the complete context needed to understand the deep dive into the linear operator dollar and its eigenvalues, which is coming next in Section 2. All right, Section 2, linear theory. This is where the mathematical heavy lifting on the operator dollar begins. Paragraph 2.1 starts by removing the phase dependence using a Fourier expansion. Equation 22 shows how the deviation till it's expanded. Eta of theta omega equals the sum from L equals minus infinity to infinity of eta sub L of omega times e to the IL theta.
Yes, this is a standard technique for problems with angular dependence. We replace the function of phase theta theta with an infinite sum of coefficients eta sub L of omega, each corresponding to a specific Fourier mode dollar. Mode of law to dollars is the average value, law to 1 is the first harmonic, law to the second, and so on.
And applying this to the linear operator transforms the PDE into a set of equations for these Fourier coefficients. Equation 23 says L theta L eta equals the sum from L equals minus infinity to infinity of L sub L eta sub L times e to the IL theta. So the action of an all theta can be understood by how each component operator, dollar operator, acts on the corresponding coefficient theta.
Exactly. It decouples the different Fourier modes, at least partially. Let's look at the operator delta while sub L defined in equation 24. Delta, omega all d, L plus pi over k, omega L to sub L eta sub L equals minus IL times the quantity omega minus ILD times eta sub L plus pi rho naught k times the quantity delta sub L comma 1 plus delta sub L comma minus 1 times the integral of d omega prime g of omega prime eta sub L of omega prime.
Okay, that dollar operator depends strongly on the mode index. The first term looks like rotation and diffusion again. L omega L, L2D L minus E L, omega eta sub L minus L squared D eta sub L. But the second term, the coupling term with the integral.
That's the crucial part. Notice the Kronecker delta symbols, delta L comma 1 and delta L comma minus 1. They are 0 unless law dollars is exactly 1 or minus 1.
So this coupling term, the part that involves interaction via dollars, only exists for the 1 and Lulladol modes.
Precisely. This is a huge simplification revealed by the Fourier decomposition. The modes $1, non-dollars correspond directly to the complex order parameter EI psi E to the IPSI and its conjugate. All other modes, load L dollars, PM2, PM3, are completely decoupled from the mean field interaction in the linearized system. They just rotate and decay due to diffusion.
So if an instability is going to happen, if synchronization is going to emerge, it must be driven by the AIT dollars 101 nuller modes. That's where the action is.
That's exactly right. The collective behavior originates entirely within this $1 log subspace in the linear regime. Also, equation 25 notes A cuv liter 1L A2 sub equals 0 is identically 0. This follows from the normalization condition, equation 14 in the paper, related to our equation 5, which essentially says the total number of oscillators is conserved, so the deviation integrated over phase must be 0.
Okay, we've established the Fourier decomposition and the structure of Lawlers, highlighting that coupling only affects when you're one other. Have we missed the strategic goal of setting this up?
No, the goal is clear. Focus the stability analysis on the Lekrodala 1 modes, because that's where any interesting bifurcation behavior must originate.
Paragraph 2.2 then introduces the necessary mathematical machinery for projections, the inner product, equation 26, and the adjoint operator, Lager, dollar, dagger. Equations 27, 28, why do we need the adjoint?
Okay, this is a bit technical but essential for the center manifold reduction later. In finite dimensions, projecting onto an eigenvector is straightforward. But in infinite dimensional function spaces like the one we're working in, finding the component of our state denita along a critical eigenvector capital Psi requires using the corresponding eigenvector of the adjoint operator, let's call it psi dagger, or psi tilde as the paper uses. The projection is then computed via the inner product, written as psi tilde, comma apta.
So the adjoint gives us the right tool to measure how much of the critical mode is present in the state.
That's a good way to think about it. The adjoint eigenvectors provide the correct basis for performing projections in this functional space. This setup is foundational for deriving the amplitude equation.
Okay, adjoint is necessary for projection. Got it. Have we covered its purpose adequately?
Yes, its role in projection via the inner product is the key takeaway. Let's move to the eigenvalue problem itself.
Paragraphs 2.3 and 2.4 set up the eigenvalue problem for the linear operator psi lambda psi equals lambda psi, equation 30. The goal is to find the eigenvalues lambda, whose real part might become positive, signaling instability.
Right. And applying the Fourier decomposition, this becomes lambda psi sub L, pi psi sub L equals lambda pi sub L for each mode dollar, where psi equals some pi sub L e to the IL theta L. The paper then makes a scaling substitution, lambda equals minus ILZ in equation, for mathematical convenience, leading to an equation for PSI involving Zeller.
And the crucial point reiterated here, non-singular eigenfunctions, exactly meaning well-behaved solutions, exist only if no nullers.
Exactly. For any mode Lambert 1, the operator is just rotation and diffusion. Lock is just nlm CD. The eigenvalues for these modes are simply lambda nlm L2D. The real part is Libby negative, or 0 if D0, but strictly negative if D0 and L is not 0. These modes are always stable and form the continuous spectrum. They don't depend on the coupling dollar or the specific shape of dilemma.
So again, any instability, any discrete eigenvalue lambda that might cross into the right half-plane must come from the Loewy-Lotter modes.
Correct. The paper now focuses entirely on the lemma dollar and by symmetry Lilleman-Goethe to find these potential instability-driving eigenvalues.
Paragraph 2.5 introduces the condition for these discrete eigenvalues. It derives the spectral function lambda sub L of lim. If we want a non-singular solution for Della when limit 1, and we're not already in the continuous spectrum, then the lim-mail related to the eigenvalue lambda by lambda must be a root of this spectral function.
Precisely. Equation 37 defines this crucial function. Lambda sub L is E, defined as 1 plus ILK over 2 times the integral of d omega prime g of omega prime over omega prime minus E minus ILD. Finding the values of z that make lambda is equivalent to finding the discrete eigenvalues lambda Ils of the full operator dollars.
So the stability of the incoherent state boils down to finding the roots of this spectral function, lambda, for 1m.
That's the essence of it. The roots Zebel of lambda determine the point spectrum, the discrete eigenvalues that can actually drive the instability.
Okay, we've defined the spectral function lambda and its role in finding discrete eigenvalues. Is its purpose clear?
Yes, it's the characteristic equation for the stability problem. Now let's look at its symmetries.
Paragraph 2.6 explores the symmetry relations of lambda z. Equation 38 shows lambdas. Lambda sub L z complex conjugate equals lambda sub minus L z star. What does this tell us?
This identity ensures that eigenvalues always come in complex conjugate pairs. If lambda is an eigenvalue corresponding to a root z, then lambda is also an eigenvalue corresponding to the root. This is standard for real operators.
But then there's equation 39, which only holds if we have the O2 symmetry, lambda, and so lambda sub L of z complex conjugate equals lambda sub L of minus z star. This looks more powerful.
It is much more powerful. This is the O2 guarantee we talked about. If z dollars is a root, this identity implies that z dollars must also be a root of the same function.
And what does that mean for the eigenvalues lambda L's?
If z-do is real, leading to a real eigenvalue lambda, this doesn't add much. But if z-do is complex, say z equals x plus iy, then z-do is plus iy with 6/8 plus, then z-do is a less plus I. Since both z-do and z-do are roots, they correspond to potentially different eigenvalues, lambda 1 and lambda 2 equals as 0. When you work it out, this means that if lambda is a complex eigenvalue, then not only is lambda also an eigenvalue from the first identity, but there's another pair related by the reflection symmetry. Specifically for the Hopf case, it forces the eigenvalue lambda to have geometric multiplicity too.
So this identity derived from O2 is the mathematical proof that the complex eigenvalue must have two linearly independent eigenvectors, CEDR, associated with it.
Exactly. This is the degeneracy that Bonilla missed. Equation 39 is the footprint of O2 symmetry directly on the spectral function, dictating the structure of the eigenvalues.
Okay, this is really getting to the heart of the O2 argument. We've defined the spectral function lambda, whose roots give the eigenvalues, and we've seen how O2 symmetry, via equation 39, guarantees the eigenvalue degeneracy, especially for complex eigenvalues leading to Hopf bifurcations. Have we fully captured the geometric interpretation here?
I believe so. Relation 39 is the mathematical manifestation of the reflection symmetry, ensuring that complex eigenvalues come with this built-in multiplicity 2 structure. Let's proceed to the projection operator needed later.
Paragraph 2.7 introduces the projection operator lambda p sub lambda onto the generalized eigenspace p sub lambda associated with an eigenvalue lambda. It's defined via a contour integral involving the resolvent operator lambda has 1 as null of lambda equals lambda minus L sub L inverse, equations 40-42. This looks like standard functional analysis machinery.
It is. The resolvent lambda is basically the inverse of lambda. It blows up when lambda is an eigenvalue. The contour integral in equation 40 is a way to isolate the part of the function leto that lies in the eigenspace, corresponding to the eigenvalue enclosed by the contour gamma dominant.
And because we know eigenvalues only occur for $1 lena, the projector simplifies. Equation 43 shows it only involved the little and lambda components, lambda a hang on 1, the a1p sub lambda a equals e to the I theta over 2pi, times integral over gamma naught d lambda prime r1 of lambda prime a1, plus e to the minus I theta over 2 pi I, times integral over gamma naught day lambda prime r minus 1 of lambda prime a minus 1. Here, ADOS is the function being projected, and $a1 are its Fourier components.
Correct. This confirms again that the critical dynamics we want to project onto live entirely within the subspace spanned by the AT and E theta modes. This projector lambda is the tool we'll use in section 3 to separate the critical dynamics from the stable ones.
Okay, we have the projector defined. Are we ready to analyze the eigenvalues based on the roots of lambda?
Yes, let's dive into the different cases.
Subsection 2.1 deals with simple roots and semi-simple eigenvalues. A simple root $z is defined by lambda 1, the lambda 1 zeta 1 family.
Yeah.
Lambda 1 prime of z naught is not equal to 0. Equation 44. This leads to semi-simple eigenvalues, meaning the number of independent eigenvectors equals the algebraic multiplicity of the eigenvalue. No generalized eigenvectors needed here.
Right, this is the generic case for codimension 1 bifurcations, where we tune one parameter like dollars.
First case, 2.1.1, real eigenvalues. This happens if the root z is purely imaginary. Let's say 0, 0, then lambda 1 z is real. This corresponds to a steady state bifurcation.
And crucially, because of the O2 symmetry, specifically equation 39 applied here, if zeta is a root, then the IOY zeta IYY descene is also a root. So we have two roots, Leo IYY and Lizu IYY. But notice lambda I1 equals IY and IY equals Y. That doesn't seem right. Let me reread that part. Okay. For a real eigenvalue lambda, the O2 symmetry ensures there are two linearly independent eigenvectors associated with it.
How does that work?
If C0 quotient 46 is the eigenvector for the real eigenvalue lambda, then its reflection kappa side, equation 48, which is just CO psi star in this case because lambda is real, is also an eigenvector for the same eigenvalue lambda, and it's linearly independent from a CO. So the eigenspace is two-dimensional.
So even for a real eigenvalue, O2 forces a two-dimensional eigenspace.
Yes, spanned by CO and its reflection the $2. The paper then explicitly constructs the corresponding adjoint eigenvectors C psi tilde in equations 49-52 and confirms they satisfy the necessary biorthogonality conditions, equations 53-54.
And the projection operator lambda eta onto this 2D space is explicitly calculated in equation 56.
Lambda eta plus lambda eta Oscillator.
Exactly. This confirms that the center manifold for a steady-state bifurcation in an O2 symmetric system is two-dimensional, described by two amplitudes, essentially corresponding to the real and imaginary parts of the order parameter deviation.
Okay, now case 2.1.2, complex eigenvalues. This happens if the root Ziller is complex, say Ziller equals x plus I with 6 Hillerboyo is complex. This corresponds to a Hopf bifurcation.
Now, the O2 symmetry equation 39 is even more critical. We know if Ziller is a root, then Zillerose is also a root. These correspond to eigenvalues lambda, a x plus I, area y, x plus lambda. They correspond to the same complex eigenvalue lambda.
So the complex eigenvalue lambda arises from two distinct roots of the spectral function. Yes, and this means that the complex eigenvalue lambda itself must have geometric multiplicity too. There are two linearly independent eigenvectors associated with lambda. The paper calls them psi and kappa psi, equation 57.
And this is the degeneracy Bonilla et al. Missed. They only considered busy.
Precisely. They missed the second eigenvector kappa cots that is guaranteed to exist by the O2 symmetry. Of course, if lambda is an eigenvalue, then its complex conjugate lambda is also an eigenvalue, coming from roots Zier and Ziel. So the full center manifold near the Hopf bifurcation point is actually four-dimensional.
Spanned by the eigenvectors for lambda, which are kappa katats, and the eigenvectors for lambda, which are papa katats.
That's the complete picture. The projection operator lambda aid given in equation 60 explicitly shows the projection onto the two modes and kappa cot associated with lambda. It has the same two-term structure as the real case, confirming the 2D nature for lambda itself, which implies the 4D nature for the lambda pair.
Okay, let's do a check here. We've clarified that O2 symmetry mandates multiplicity to semi-simple eigenvalues for both real, steady-state, and complex Hopf codimension 1 bifurcations. This confirms the need for a two-dimensional for real lambda or four-dimensional for complex lambda pair center manifold description. Have we clearly traced the connection between the spectral function roots lambda and this eigenvector multiplicity dictated by O2?
Yes, I think we have. We saw how a simple root dollar combined with the O2 symmetry identity, 39, forces the existence of two linearly independent eigenvectors, in kappa L, for the resulting eigenvalue lambda. This holds whether lambda is real or complex. Now let's move to the non-semi-simple case where things get more complicated.
Subsection 2.2 deals with multiple roots and non-semi-simple eigenvalues. This happens when the root dollars is not simple, meaning lambda 1 and lambda was a dollars. In this case, we need generalized eigenvectors. What are those?
A generalized eigenvector upsilon, capital Epsilon, is a vector that's not quite an eigenvector itself, but lambda I, upsilon minus lambda I, times upsilon, is a true eigenvector, a C, instead of being 0. So lambda epsilon plus C. They form Jordan-James. These arise when the algebraic multiplicity of an eigenvalue, many times it's a root, is greater than its geometric multiplicity, how many independent eigenvectors it has.
And the paper shows that such a generalized eigenvector upsilon exists for this system only if the root Ceval is non-simple, i.e. if lambda 1's lambda would certain 67.
Exactly. This double root condition lambda 1 auxiliary equation 68 is the mathematical signature of the Takens-Bogdanov point, assuming zeros is imaginary, so lambda is real.
So the Takens-Bogdanov bifurcation occurs precisely when the real eigenvalue becomes non-semi-simple.
That's right. It's a collision of eigenvalues on the real axis that results in this non-semi-simple structure. The paper then explicitly constructs the true eigenvector equation 70 and the generalized eigenvector upsilon, equation 71 for this situation. And due to O2 symmetry, the reflections kappa quietus psi and ebb psi upsilon must also exist.
So the critical space is now spanned by 4 vectors.
Yes. At this highly degenerate point, the center manifold associated with the real eigenvalue, lambda dollar, is 4-dimensional, spanned by 2 eigenvectors and 2 generalized eigenvectors, upsilon, upsilon.
The paper then constructs the corresponding adjoint system, yielding an adjoint eigenvector, equation 72, and a generalized adjoint eigenvector, upsilon tilde, equation 73, and lists the necessary biorthogonality relations, equation 74-77, which are quite complex.
They are needed to correctly project onto this 4D space.
And finally, the projection lambda eta for this non-semi-simple case is calculated, equation 84. It explicitly shows the 4 components involving the amplitudes projected onto Siena and upsilon and their reflected counterparts.
Confirming the 4-dimensional structure.
Okay, mandatory check. This raises an important question. Why did we spend so much time on these generalized eigenvectors and the non-semi-simple case? The paper focuses on the codimension 1 steady state and Hopf bifurcations, which were semi-simple.
Great question. Because the merger point of the steady state and Hopf bifurcations, the Takens-Bogdanov point identified in the abstract, is defined by precisely this non-semi-simple real eigenvalue condition, lambda 1 0 cup equals 0. Understanding this structure, especially the 4-dimensional space spanned by psi, upsilon, kappa dot poli psi, kappa dot epsilon, is absolutely essential for understanding where the 2 simpler codimension 1 bifurcation lines meet in the parameter space. It's the gateway to the most complex dynamics discussed.
Okay. So understanding the non-semi-simple case is key to understanding the junction point between the simple cases. Makes sense.
Exactly. Now let's apply this theory to the specific example.
Subsection 2.3 applies all this linear theory to the specific example mentioned in the abstract. A bimodal population described by a frequency distribution g omega, which is the sum of 2 Lorentzians, equation 85, peaking at the omega pm omega 2 equals plus or minus omega naught, with a width parameter epsilon.
Right. For this specific g omega, the integral in the spectral function lambda 1 blot can actually be calculated analytically using residues. This leads to an algebraic equation for the roots.
And the result, equation 88, shows there are generally 2 roots, happen plus is a plus and Zillowi minus, which can be real or complex depending on the parameters, specifically how the peak separation for omega dollars omega naught compares to the coupling dollars.
Yes, and this allows the paper to map out the different regions of stability and instability in the parameter space defined by dollar and pomega, implicitly shown in figure 1.
It identifies the key parameter boundaries where things change, k equals k sub e, where eigenvalues might disappear into the continuous spectrum. Jk equals k sub c, where real eigenvalues cross the imaginary axis. The steady-state bifurcation threshold, equation 90. K4 omega k equals 4 omega naught, where the two roots collide, potentially leading to the non-semi-simple case, kkk equals k sub h, where complex eigenvalues cross the imaginary axis, the Hopf bifurcation threshold equation 91.
Exactly. Plotting these boundaries, kcd omega to epsilon and khd omega to epsilon in the ticket omega plane gives the stability diagram.
And it notes the codimension 2 point where the steady-state and Hopf boundaries meet. This occurs when k4 epsilon plus d equals 4 times epsilon plus d, and the omega to 2 bellers epsilon plus d tot omega naught squared equals epsilon plus d squared, which corresponds to omega naught plus d omega naught equals epsilon plus d. This is the Takens-Bogdanov point for this specific model.
Yep, the point where lambda 1 z gabella occurs right there.
The subsection concludes by summarizing the types of instabilities found as you change parameters. For small megadollars, you get the steady-state bifurcation first as you increase Tox dollars. For larger megadollars, the Hopf bifurcation happens first, leading to oscillations, specifically the stable standing waves that Kuramoto had hypothesized.
Setting the stage perfectly for the nonlinear analysis in Section 3, where the stability of these states, standing waves versus traveling waves, will be determined.
Okay, mandatory check for Section 2. We've completed the entire linear theory section. We established the general mathematical framework using Fourier modes, defined the spectral function lambda and its roots, analyzed the crucial role of O2 symmetry in determining eigenvalue multiplicity, semi-simple cases, explored the non-semi-simple eigenvalue structure at the Takens-Bogdanov point, and applied all this to map out the specific linear stability phase diagram for the bimodal Lorentzian population example. Have we missed any crucial details regarding the structure of the spectrum or the setup for the nonlinear analysis?
No, I think we've thoroughly unpacked it. We've clearly shown how the spectrum is determined by the discrete eigenvalues, roots of lambda, which drive the instability, emerging from the background sea of the continuous spectrum, damped modes for lambda Armand and a long text-free dollar. This provides the complete linear picture required before tackling the nonlinear dynamics and stability calculations in Section 3.
All right, Section 3. This is where we derive the amplitude equations that tell us what happens after the instability threshold is crossed. Paragraph 3.1 starts by considering the Fourier expansion of the nonlinear term from equation 11.
Right. Equation 95 shows the structure. Eta involves products of the deviation, meta, and its derivatives. When expanded in Fourier series, these quadratic and higher order terms will couple different Fourier modes together. For example, a product of an ln$ mode and an ln$ mode can create an LL$ mode and a little dollar mode. A product of LL$ and older mode can create LL$ and a level mode.
So the nonlinearity mixes the modes.
Exactly. While the linear operator kept the idol and modes somewhat separate, the nonlinear term creates couplings between the critical one-to-dollar modes and all the other stable higher harmonic modes. This coupling is essential for calculating the saturation and stability of the bifurcating solutions.
Okay, let's get into the first case. Subsection 3.1, steady-state bifurcation, pages 21-28. This occurs when a real simple eigenvalue lambda crosses 0 at kith. We know from Section 2 that the center manifold, the critical subspace, is two-dimensional, spanned by the eigenvector kara and its reflection kappa arc she.
Right. The idea of center manifold reduction is to express the full state Kela as a combination of components within this 2D critical space and components orthogonal to it, the stable modes. We write theta alpha psi plus psi equals alpha psi plus alpha star psi star plus s, where alpha of t is the complex amplitude of the critical mode pair, and psi dal represents the contribution from all the stable damped modes.
The analysis then decomposes the full evolution equation lita plus n into separate equations for the amplitude alpha and the stable part part. Equations 96-102. The goal is to get a closed equation for alpha TDO.
Yes. The core assumption of the center manifold theorem is that near the bifurcation, the fast, stable modes rapidly adjust to whatever the slow, critical amplitudes alpha are doing. So we can assume Zeller is effectively a function of the amplitudes. Zeller effectively h alpha SC equals h of alpha, alpha star, equation 103. The function dollar represents the enslaved stable modes.
Subsection 3.1.1 focuses on the dynamics on this center manifold. Because of the O2 symmetry, the evolution equation for the complex amplitude alpha must take a specific constrained form.
Right. O2 symmetry dictates that the dynamics must be expressible in terms of the O2 invariant quantity, which for this 2D space is sigma equals magnitude alpha squared. The resulting amplitude equation must have the form alpha PDO, alpha dot equals P of sigma times alpha, equation 108, where it analyzes some complex function initially.
But wait, lambda's real here. Doesn't that simplify Peeler?
Good point. Since lambda is real, steady-state bifurcation, the coefficient p sigma must also be real. Expanding it near sigma dollars, we get the final amplitude equation, equation 109, alpha lambda plus p sigma plus alpha 2 plus alpha dot equals alpha times the quantity lambda plus p sub sigma of 0 times magnitude alpha squared plus order magnitude alpha to the fourth. Here, lambda is the linear growth rate proportional to k-sig, and sigma p sub sigma of 0 is the crucial cubic coefficient.
As the stability of the synchronized state that emerges is determined by the sign of this one number.
Exactly. If t $, the cubic term is stabilizing. As lambda becomes positive, i.e. keep up on tech the dollar, the cubic term is stabilizing. As lambda becomes positive, i.e. $, this is a supercritical bifurcation. If p sigma 0, the cubic term is destabilizing, leading to unstable growth. This is a subcritical bifurcation, often associated with hysteresis.
Okay, the O2 constraints simplify the amplitude equation down to this form, depending only on alpha 2 other. The paper then details how symmetry also constrains the form of the enslaved modes function, Autobader, equations 116, 120, showing dollars must be composed of terms like alpha HL awashula alpha to the LH sub L of omega, sigma.
Yes, these constraints are needed to actually calculate sigma.
Let's check comprehension here. We've set up the center manifold reduction for the steady-state case, used O2 symmetry to get the form of the amplitude equation alpha lambda plus tcon alpha 2 else, and identified sigma as the key coefficient determining stability, supercritical versus subcritical. Is the logic clear?
Yes, the logic flow is clear. Now the task is to actually compute sigma.
Subsection 3.1.2 tackles the evaluation of sigma 26. How is this done?
It's done by substituting the expansion eta alpha psi plus h, alpha alpha, back into the full Fokker-Planck equation alpha plus ne. Then you systematically collect terms of the same order in alpha. The coefficient sigma arises from the interplay between the quadratic part of the nonlinear term, nlda, and the linear operator dollar acting on the quadratic part of the stable mode function, dela.
So LA has terms like eta on the process. This creates terms proportional to alpha psi 2 day. These terms act as a source or forcing term for the higher Fourier modes within the stable function depth.
Exactly. The analysis shows that the crucial component needed is the Helle-2-Tark-Cotter Fourier order alpha theta approxa alpha 2 ht2 of phode is approximately alpha squared h sub 2 superscript 2 of omega e to the I2 theta. The coefficient 2h2 sub 2 superscript 2 of omega is found by solving a linear equation forced by the quadratic nonlinearities, equation 129.
And the solution for this crucial coefficient is given in equation 131.
Right.
2 pax gay psox sub 2 superscript 2 of omega equals minus I pi psox sub 1 of omega over omega minus c naught minus I2d. Note pohai is the L-dollar component of the eigenvector CE.
Right. Once you have two echelons, you can plug it back into the equations and the coefficient sigma pops out. The final expression is given in equation 132. Sigma lambda in TSI1 omega plus TSI1 simplified form based on context. Actual formula involves more terms derived from the lambda, but structure is similar. The key is it depends on an integral involving the frequency distribution, the eigenvector components, p psi EC, the spectral function derivative, lambda 1, and the parameters d, z dollars.
And the paper emphasizes that, although derived from complex quantities, sigma 0 must be real due to the O2 symmetry constraints, which provides a consistency check. Okay, we have the formula for Pisma. How we trace the origin quadratic nonlinearities forcing Will-2-Calder stable modes, which then feed back cubically onto the Teller-1 critical mode.
Yes, that's the mechanism. Quadratic terms in N force quadratic terms in H, which then interact with L and N again to produce cubic terms in the amplitude equation for alpha.
Subsection 3.1.3 applies this formula to the bimodal Lorentzian example, equation 85, along the steady-state bifurcation curve, KKCL.
Yes. For that specific omega, the integral for figma can be evaluated. The result is given in equation 133, an explicit, though complicated expression in terms of the parameters epsilon d omega dollar.
And the sign of sigma.
The sign turns out to depend on the comparison between the peak separation squared omega $2 and critical value omega 2 omega sub d squared, which depends on epsilon and dollars. If omega dollar peaks are close together, then sigma and the bifurcation is supercritical. The synchronized state is stable. If omega dollar peaks are far apart, then sigma dollars and the bifurcation is subcritical. The synchronized state that emerges is initially unstable.
That's a really interesting result. The stability depends directly on how separated the two subpopulations are.
It is. It shows that just achieving synchronization isn't enough. Its stability depends critically on the underlying population structure.
Okay, we have the stability result for the example. Now, subsection 3.1.4 revisits the zero noise limit, 0 to dollars, for this coefficient sigma.
Right. This connects back to the abstract's claim about contrasting with Vlasov systems. Does the sigma blow up as 0 to dollar?
The analysis shows that while the integrand might look problematic as 0 to 2, because of the root 0, it also goes to 0, putting poles near the real axis, Using careful analysis with Plumage formulas, which relate integrals across singularities to principal values and residues, the final result for sigma remains finite.
So, unlike the Vlasov-Poisson case where coefficients often diverge like zero time, here the cubic coefficient behaves well in the zero noise limit. This reinforces the robustness of the bifurcation prediction.
The resulting expression for sigma 2 duto is given, equation 139. For a typical unimodal symmetric profile du omega, like a single Gaussian or Lorentzian, this formula predicts zero null.
Meaning that for simple unimodal populations, the steady-state synchronization transition is generally expected to be supercritical stable in the weak diffusion limit.
Okay, Vlasov contrast confirmed again for the cubic coefficient. Finite result is du Ortaler.
Yep.
Finally, subsection 3.1.5 briefly discusses perturbing the symmetry from O2 down to SO2 by breaking the reflection symmetry.
If you break the reflection symmetry, the O2 constraints are lifted. The analysis, not done in detail here, shows that the real eigenvalue lambda $0 typically splits into a complex conjugate pair near zero. This means the steady-state bifurcation is destroyed and replaced by a Hopf bifurcation, leading to time-dependent solutions like traveling waves even when you expected a steady state. Symmetry breaking can drastically change the outcome.
Interesting. Okay, mandatory verification for the steady-state section. We've analyzed the steady-state bifurcation in depth. We derived the amplitude equation form using O2, calculated the crucial cubic coefficient sigma, applied it to the bimodal example, finding regions of supercritical and subcritical behavior depending on omega dollars, confirmed the coefficient remains finite as 0 to dollars, unlike Vlasov, and briefly touched on symmetry breaking. Have we missed any connections or key aspects of the steady-state analysis?
No, I think we've thoroughly unpacked it. We understand how the synchronized state emerges and what determines its stability in this case. The next logical step is applying the same center manifold reduction machinery to the complex eigenvalue case, the Hopf bifurcation.
All right, subsection 3.2. Hopf bifurcation, pages 29 and 41. This is the core of the paper's corrective argument. Here, a simple complex eigenvalue lambda, basing lambda next round, crosses the imaginary axis at the critical coupling collars.
And as we established in section 2 using O2 symmetry, this eigenvalue lambda has multiplicity 2. The center manifold is therefore four-dimensional, spanned by the two eigenvectors for lambda and kappa psi, and the two eigenvectors for lambda rsi, and the two eigenvectors for lambda xi.
The state beat is now decomposed using two complex amplitudes. Alpha c associated with c, or beta of t associated with the reflected mode kappa c. So eta alpha c plus cc plus eta equals alpha c plus beta kappa c plus complex conjugate plus s, where cc means complex conjugates of the preceding terms, and c day is again the stable part.
And beta is the amplitude corresponding to the mode that Bonilla t neglected, including it is essential. The projection needed to define beta is beta beta t equals inner product kappa to t to comma eta.
Equations 140-148 set up the decomposition into these critical modes, alpha, beta, and the transverse stable modes, C.
Same strategy as before. Assume Salar is a function of the critical amplitudes, h alpha alpha beta s equals h of alpha alpha star beta beta star, equation 149, and derive the coupled equations for data alpha beta dot into pages 150-151.
Subsection 3.2.1 works out the dynamics on the center manifold. Again, O2 symmetry imposes strong constraints. How does O2 act on these amplitudes alpha and beta?
The transformations are given. Rotation by angle theta, e I phi dot a phi dot alpha beta equals e to the minus I phi alpha comma e to the I phi beta. Alpha rotates one way, beta rotates the other. Reflection alpha dot alpha beta equals beta comma alpha. Reflection swaps the amplitudes.
These symmetries, plus an implicit phase shift symmetry, drastically restrict the form of the coupled amplitude equations, d alpha and avo. The theory of O2 equivariant Hopf bifurcations shows the dynamics can be reduced to a standard normal form.
Yes, the normal form depends only on specific combinations of the amplitudes that are invariant under these symmetries. The key invariants turn out to be $1 alpha 2 plus beta 2 UEQ equals magnitude alpha squared plus magnitude beta squared related to the total intensity, and delta beta 2 alpha 2 delta equals magnitude beta squared minus magnitude alpha squared related to the difference or imbalance.
The resulting normal form equations, after removing some higher order terms via coordinate transformations, are given in terms of these invariants. Equation 165 implicitly leads to 168, 169. Ultimately, they can be written as two coupled equations for the real amplitude sextant alpha and sextant lotus beta, plus p0 by 12 plus by 1 to 12 plus p0 by 1 plus 1 textual 2 plus q0 by 12 plus p0 by 22, 2. These are derived from 168, 169.
Right. Here, textual part lambda is the linear growth rate, proportional to k. And now we have two crucial cubic coefficients, p sub u of 0 and the free outers of 0. These determine the stability and type of the resulting oscillatory solutions.
What kinds of solutions do these equations predict?
Analyzing the fixed points of these equations for 6 by dollars by 2 reveals two main types of non-zero solutions, summarized in Table 1. Traveling waves, TW, either 1 by 1 by 2 by 2 equals 0 or 10 dollars by 2 number 1. This corresponds to only one of the modes, PS or kappa-tex, being excited. Physically, it's a single synchronized clump circulating. Standing waves, 6 by dollars by $2. Both modes and kappa-tex are excited equally. Physically, this corresponds to two counter-propagating synchronized clumps, or a single clump whose amplitude breathes periodically.
And the stability of these TW and SW solutions depends entirely on the values of Penn dollars and
Entirely. The conditions are summarized in the text and Figure 2. For example, for the SW to be stable, you typically need PO into the TW to be stable. You need pure QO plus some dollars. They compete.
And the oscillation frequency omega capital omega of these waves near the bifurcation point is given by the imaginary part of the eigenvalue lambda plus corrections involving the amplitudes, equation 170.
Correct.
Okay, comprehension check. For the Hopf case, O2 leads to a 4D center manifold with amplitudes alpha, beta. Symmetry reduces the dynamics to a 2D system for alpha, beta governed by coefficients Puto and $3. This system predicts two solution types, TW, one mode excited, and SW, both modes excited equally. Their stability depends on Putar and $3. Is that summary accurate?
Perfectly accurate. The structure is clear. Now we need to calculate those coefficients.
Subsection 3.2.2 evaluates Putam on $3, pages 34-37. This involves calculating the cubic terms in the original alpha equations and then performing coordinate transformations, near identity changes of variables, to eliminate terms that don't respect the phase shift symmetry, arriving at the normal form coefficients.
It's a standard but tedious procedure in bifurcation theory. The final coefficients are expressed in terms of integrals involving the quadratic components of the center manifold function, similar to how sigma was calculated in the steady-state case, equations 177 and 178.
The calculation requires finding three different quadratic components of DL-2, denoted H21, H sub 2 superscript 2, H sub 2 superscript 1, H sub 2 superscript 0, which are forced by different combinations of the alpha and beta step terms in the quadratic part of DLSX and DLR79.
Yes, the solutions for these twinaptic components are found by solving linear equations, equations 183, 185. They involve integrals of the eigenvector and its reflection conjugates.
And again, the paper revisits the Vlasov contrast. Just like sigma, these coefficients Po and here and 2I are shown to remain finite as the noise Diller to other.
Reinforcing the key message. The predicted stable oscillations in this Kuramoto system are robust and expected to exist even in the absence of noise, unlike the situation in some Vlasov models where analogous coefficients might diverge.
Okay, we have the formulas for Po or other and confirmation of their finiteness. Ready for the example application?
Let's see the results.
Subsection 3.2.3 applies these coefficient formulas to the bimodal Lorentzian population example, evaluated along the Hopf bifurcation curve, KK.
This is the moment of truth for stability. The signs of $dollar for this specific model will tell us whether the TW or SW is stable.
The analysis involves evaluating the integrals using the explicit forms of Xi omega for the 2 Lorentzian case. The paper notes that by inspection of the resulting formulas, equations 189-191, certain real parts are positive.
This leads to the conclusion that PUR is negative and PUR is also negative. This means both the TW and SW solutions emerge supercritically. They exist for Ki.
So both exist. Which one wins? Which one is stable?
The stability is governed by the sign of 3. The calculation shows that $3 contains a term pu epsilon d omega notus of epsilon d omega naught squared given in equation 192, which is explicitly shown to be positive. This ensures that $3 itself is always positive for this model.
And what does $2 imply for stability combined with $2?
Consulting the stability conditions for the O2 Hopf normal form, often shown in diagrams like Figure 2. Standing waves, SW. Stability requires $4 and $4. Since we found $4 and $4, this condition $4 is satisfied. Therefore, the standing waves are supercritical and stable. Traveling waves, TW. Stability requires $2, which we have, and $2 plus R0 duo. However, since 3 is positive, if it's large enough, $2 plus R0 could be negative. More directly, the analysis shows the relevant eigenvalue governing TW stability is proportional to $2. Since $3, this eigenvalue is negative, meaning the TW solution is unstable relative to the SW. So the traveling waves are supercritical and unstable.
There it is. The definitive result based on the O2 analysis for the bimodal population. Stable standing waves, unstable traveling waves.
Precisely.
Subsection 3.2.4 explicitly compares this to the work of Bonilla, New, and Spigler.
It confirms the correction. Bonilla et al.'s analysis, by neglecting the beta mode, equivalent to setting 6 by $2 from the start, effectively only looked at the dynamics along the step-roulette axis, equation 194. This led them to predict a single stable solution, the traveling wave, because they completely missed the competing standing wave state and the instability induced by the $2 term that couples the two modes.
Their simplification removed the crucial competitive dynamics.
Exactly. They failed to see the dominant stable SW state and the inherent instability of the TW state within the full O2 symmetric framework.
Subsection 3.2.5 compares the results to Okuda and Kuramoto's study of two coupled populations.
It shows that the OK model is essentially a special case of Crawford's general Fokker-Planck model when the Lorentzian with epsilon dollars delta function frequency distributions and the couplings are chosen appropriately, equations 201, 202. OK's results, which did find stable SW, are therefore consistent with Crawford's more general and rigorous O2 analysis.
Okay, consistency check there. And finally, subsection 3.2.6 mentions perturbing O2 to SO2 again. What happens to the Hopf bifurcation?
If you break the reflection symmetry, the multiplicity 2 complex eigenvalue lambda splits into two distinct complex conjugate pairs, generally with slightly different real parts. This means the single O2 Hopf bifurcation point NASA dollar splits into two distinct Hopf bifurcation points. The standing waves, which required the perfect O2 symmetry, equal excitation of Assazi and kappa fucta, typically perturb into more complex modulated waves.
So the clean SWTW picture relies heavily on the perfect symmetry.
It does. Breaking the symmetry complicates the dynamics significantly.
All right, mandatory verification for Section 3. We have meticulously derived the amplitude equations for both steady state and Hopf bifurcations using center manifold reduction and O2 symmetry. We applied these to the bimodal population, confirming the stability hierarchy predicted in the abstract. Stable synchronized state, if supercritical, or stable standing waves, with traveling waves being unstable in the Hopf case. Have we secured the main finding regarding the stability correction and the role of O2?
Yes, I think we've thoroughly unpacked it. The correction demonstrating that O2 symmetry forces the coexistence of stable standing waves and unstable traveling waves near the Hopf bifurcation, thereby resolving the discrepancy with Bonilla et al., is the central takeaway of this detailed nonlinear analysis. We've seen why it happens mathematically.
Okay, Section 4, Discussion. This section wraps things up. Paragraph 4.1 refers to Figure 4, which summarizes the stable nonlinear states found in the parameter space. The incoherent state, stable at low k, the partially synchronized state, stable after a supercritical steady state bifurcation, and the standing waves, stable after the Hopf bifurcation.
Right. It provides a visual summary of the main results. However, the paper explicitly states it has not treated the boundary between the stable partially synchronized state from the steady state branch and the stable standing waves from the Hopf branch. That boundary is shown as a dashed line in Figure 4. Analyzing that transition is left for future work.
And the discussion highlights the major challenge for future work, analyzing the dynamics near the O2, Takens-Bogdanov bifurcation point where the steady state and Hopf lines merge.
Exactly. This point represents a highly degenerate bifurcation. The analysis is complicated further because in the specific bimodal example studied, the steady state bifurcation becomes subcritical near the merger point.
Why does it make it harder?
Because the standard normal form theory for the O2, Takens-Bogdanov bifurcation, developed by Dengelmeyer and Knobloch, cited in the paper, assumes the steady-state branch is supercritical. The subcritical nature here means that higher-order nonlinear terms, quintic or even septic, likely become important to stabilize the dynamics. This might even push it into the territory of a codimension 3 bifurcation, requiring analysis beyond the cubic terms calculated in this paper. It's a significantly more complex mathematical challenge.
So the paper solves the codimension 1 problems rigorously, but points towards the deep complexity waiting at the codimension 2 junction.
Precisely. It lays the groundwork and identifies the next major theoretical hurdle.
Okay, mandatory check for the discussion. We've covered the summary of stable states, Figure 4, the identification of the untreated PSSW boundary, and the highlighting of the O2 Takens-Bogdanov point, especially complicated by subcriticality, as the key area for future, more advanced analysis, possibly involving higher-order nonlinearities. Have we missed any nuances in the paper's final conclusions or directions for future work?
No, I think we've thoroughly unpacked it. The primary task outlined in the abstract, analyzing the instabilities near the incoherent state using amplitude expansions, is complete. The discussion correctly identifies the boundaries of the current analysis and the next steps needed for a full picture. #tag processing final sections, pages 42-46.
All right, let's quickly process the final administrative sections to ensure full, unabridged protocol adherence. Section 5, Acknowledgements.
Here, Crawford notes helpful conversations, particularly with Stephen Strogatz, another major figure in this field. Standard academic practice.
Okay, acknowledgements noted. Section 6, Figure Captions.
These briefly describe the content of the figures. Figure 1 shows the boundaries, Kelly-CHA, etc., in the parameter space for the bimodal example. Figure 2 illustrates the different stability regions for the Hopf bifurcation depending on the signs of pup and $3. Figure 3 compares frequency predictions. Figure 4, the summary phase diagram of the stable nonlinear states, incoherent, PS, SW.
Captions reviewed. They match our understanding of the figure's roles. Section 7, References.
This lists the cited works, providing crucial historical context. Papers by Winfrey, Kuramoto, Sakaguchi, Strogatz and Marolo, Bonilla et al., Okuda and Kuramoto, and references for the supporting mathematical theory, like bifurcation theory texts by Golubitsky et al., functional analysis like Reed and Simon, center manifold theory, essential for placing the work in context.
References noted. That seems to cover all numbered sections of the paper itself. Have we missed any part of the document structure?
No, from title to references, following the linear progression, I believe we've covered the entire document structure as presented. #tag outro.
Well, that was an immensely detailed journey, an unabridged deep dive through one of the great foundational papers in the dynamics of coupled oscillators. We started with, well, essentially a description of chaos, the incoherent state, and we emerged with a really robust understanding of how stable synchronization and collective oscillations can arise.
It was quite the trip through bifurcation theory. I think the 3 key intellectual takeaways are really crucial for anyone studying emergent phenomena in complex systems. First, that Vlasov contrast we kept hitting.
Right.
The Kuramoto-Fokker-Planck system is mathematically robust in a way some other kinetic theories aren't. Its stability coefficients, the things determining what happens after instability, remain finite, even when you hypothetically remove all external noise. $0. The predictions hold up.
That's a big one. Second takeaway.
The absolute necessity of respecting physical symmetry. We saw time and again how the O2 circular symmetry, present when the frequency distribution is balanced, wasn't just a detail. It requires the complex eigenvalue at the Hopf bifurcation to have multiplicity too.
Forcing the coexistence of 2 wave solutions.
Exactly. And ignoring one of those modes, the reflected one, as previous researchers apparently did, simply yields the wrong stability prediction. You need the full picture dictated by symmetry.
And the third takeaway is that stability results itself, the correction.
Yes. For the bimodal populations analyzed, the stable oscillation mode that emerges from the Hopf bifurcation is the standing wave, that rhythmic breathing of synchronization. The seemingly simpler circulating traveling wave is actually mathematically unstable in this O2 symmetric case. Getting that hierarchy right was the paper's major contribution to the nonlinear dynamics.
Which leaves us with this provocative thought for you, the listener, to consider. We saw that the stability and the very type of synchronized state depend exquisitely on the details of the frequency distribution omega, things like whether it's unimodal or bimodal, how spread out it is, its symmetry. We also touched on that highly degenerate, mathematically complex Takens-Bogdanov point, where steady synchronization and oscillatory synchronization meet. So the question is, what real-world physical systems, maybe populations of neurons firing in the brain, maybe arrays of coupled lasers or mechanical resonators, maybe even social systems, might operate near that delicate, high codimension Takens-Bogdanov point? Where might we find systems poised right at that critical crossroads, where the entire nature of their collective behavior hangs in a delicate balance, ready to tip into either steady synchrony or complex, perhaps chaotic oscillation, depending on the tiniest changing conditions?
A fascinating question about where such critical complexity might manifest itself in the real world.
Indeed. That concludes this deep dive.
Welcome to the Deep Dive, where we extract the core knowledge from the most formidable source material. Today, we're undertaking a deep exploration into the very foundation of synchronized dynamics. The mathematics that explains how millions of decentralized units suddenly begin to move as one.
That's right. We are diving into a monumental work of mathematical physics. John David Crawford's 1993 paper, Amplitude Expansions for Instabilities in Populations of Globally Coupled Oscillators. This paper isn't just theory, it's really a necessary corrective. Crawford uses highly rigorous tools, bifurcation theory and center manifold reduction, to settle a key debate and fundamentally reshape our understanding of synchronization onset in large populations.
And our mission is, well, uncompromising. We are going through this document with extreme granularity, but we are doing it conversationally. We're breaking down the science, the math, and the underlying logic, ensuring that we understand not just what was found, but why every mathematical step was necessary to achieve that finding.
Exactly. To frame this deep dive, the paper addresses the moment synchronization begins, that transition from an initially disordered or incoherent state to collective order. And this understanding is critical across biology, engineering, even physics.
Okay, so the paper is foundational, authored by John David Crawford from the Department of Physics and Astronomy at the University of Pittsburgh. Let's start right at the beginning, processing the abstract. #, processing the abstract, linear progression and granularity. The first sentence. We analyze the nonlinear dynamics near the incoherent state in a mean field model of coupled oscillators. Okay, this immediately establishes the domain. Why must the dynamics be nonlinear? What does that really buy us here?
Well, they have to be nonlinear because synchronization itself is fundamentally a nonlinear outcome. If the system were linear, any initial disturbance would either just grow without bound or simply decay away. Synchronization, though, it's about stable, self-sustaining collective behavior, the whole being more than the sum of its parts, essentially. And that absolutely requires nonlinear feedback.
Right, like the interactions change depending on the state itself.
Precisely. And we're focusing specifically on the behavior near this incoherent state, which is basically the equilibrium where all the oscillators are just randomly scattered in phase. There's no net macroscopic order. R is 0.
And the mean field model, that's the standard trick for dealing with huge numbers, right?
Exactly. When the number of oscillators, non-dollars, is potentially astronomical, we can't possibly track each one. The mean field approximation lets us assume each oscillator interacts equally with the average state, the field of the entire population. So instead of the dollar-complicated individual equations, we get a single statistical equation describing the overall distribution. Much more tractable.
Okay, so that sets the goal in the basic model. Have we fully unpacked that first sentence? Any nuances left?
I think that covers it. Nonlinearity near the incoherent state using a mean field approach sets the stage perfectly. Let's move to the second sentence, which is quite a bit denser. It defines the mathematical approach.
It reads, the population is described by a Fokker-Planck equation for the distribution of phases, and we apply center manifold reduction to obtain the amplitude equations for steady state and Hopf bifurcation from the equilibrium state with a uniform phase distribution.
Whoa, okay. Lots to unpack there.
Yeah, we absolutely have to pause here. This sentence lays out the entire mathematical toolbox. First up, the Fokker-Planck equation. What is it? It's a partial differential equation. It comes straight out of statistical mechanics. It governs how the probability density function, that's the distribution of oscillator phases, evolves over time.
And why use this instead of just tracking individuals? Because N is huge.
Precisely because non-dollar is assumed to be effectively infinite, we're in the continuum limit.
Sure.
The Fokker-Planck equation is perfect because it handles both the deterministic forces, like the coupling trying to pull oscillators together, and the random forces like external noise, which manifests as diffusion in phase space. Okay, so it's the master equation for the population's statistical behavior, handling both order and randomness. Now, what about center manifold reduction? How does that help solve this, presumably very complex Fokker-Planck equation?
Right, center manifold reduction is a really powerful technique from dynamical systems theory. The core idea is this. When a system loses stability, when a bifurcation happens, it almost never happens across all possible directions or modes at once. It tends to concentrate over just a few critical, slow directions.
Okay, so it's like finding the weak points where the change actually happens.
Exactly. The center manifold theorem provides the mathematical machinery to isolate precisely those critical directions. It lets us effectively collapse the infinite-dimensional Fokker-Planck system down to just a handful of much simpler finite-dimensional equations called amplitude equations. These capture the essential long-term dynamics right near that instability point. It's a massive simplification.
And the paper mentions two specific types of instabilities or bifurcations it's looking for using this method.
Yes, two key types. First, Steady-state bifurcation. This is where the system transitions from the equilibrium, the incoherent state, to a new, stable, but time-independent synchronized state. Think of it as the oscillators locking into a fixed pattern, so the order parameter R becomes positive and constant.
Okay, a static synchronized state. And the other?
The other is Hopf bifurcation. This is where the system transitions to a stable but time-periodic state. This usually manifests as some kind of wave or sustained collective oscillation. The order parameter R might oscillate, for instance. Both of these instabilities emerge from the equilibrium state, which the sentence reminds us is characterized by a uniform phase distribution. Mathematically, that's just the same thing as the incoherent state.
Right, the baseline where nothing is happening collectively. Okay, I think that meticulously covers the mathematical framework. Fokker-Planck for the population, center manifold to simplify, looking for steady state and Hopf bifurcations emerging from the uniform distribution. Does that seem complete for sentence 2?
Yeah, I think we've thoroughly unpacked it. We understand the what and the why of each mathematical tool mentioned. Let's proceed to the third sentence, which introduces a really critical constraint.
Sentence 3. When the population is described by a native frequency distribution that is reflection symmetric about 0, the problem has circular symmetry. Okay, symmetry, always important in physics and math.
Hugely important here. Reflection symmetric about 0 means the distribution of the oscillator's natural frequencies, g omega, is an even function. Mathematically, g omega. What this means physically is that for every oscillator that naturally wants to spin clockwise, positive omega, there's a statistically identical counterpart that wants to spin counterclockwise, negative omega.
So a perfect balance.
A perfect balance. And this condition confers what's called O2 symmetry on the problem. That's circular symmetry, which includes both continuous rotations, shifting all phases by the same amount, and reflections, flipping the sign of phases and frequencies. This O2 constraint is absolutely essential because, as we'll see, it dictates things like the degeneracy of the eigenvalues, how many ways the system can go unstable at once. And ultimately, it's the key to correcting some prior results on stability.
Okay, that sets up the crucial role of symmetry. Let's proceed to sentence 4. This one seems to deliver a key finding by contrasting with other fields. In the limit of 0 extrinsic noise, although the critical eigenvalues are embedded in the continuous spectrum, the nonlinear coefficients in the amplitude equation remain finite in contrast to the singular behavior found in similar instabilities described by the Vlasov-Poisson equation.
Right, here's where it gets really interesting intellectually. The paper draws a direct comparison to systems described by the Vlasov-Poisson equation, think collisionless plasmas or even gravitational systems. Those systems often exhibit a phenomenon called Landau damping, which is a kind of collisionless damping mechanism.
Okay.
Now, if you try to perform a stability analysis on those Vlasov instabilities, particularly as you take the damping parameter, which is analogous to the noise dollars here, down towards 0, the key nonlinear coefficients in the resulting amplitude equations often blow up. They become singular, sometimes diverging really sharply, like T3all.
So the math itself breaks down. The standard stability analysis doesn't work in that limit for Vlasov systems?
Essentially, yes. It requires extremely specialized and complex mathematical methods just to handle that singularity. What Crawford demonstrates here is a fundamental difference. For the Kuramoto system, described by Fokker-Planck, even though it shares some complexity with Vlasov systems, like having critical modes embedded in a continuous spectrum of damped modes, the crucial nonlinear coefficients that determine stability remain finite as the noise dollar goes to 0. So the Kuramoto system is more mathematically robust in this sense. Precisely. That's a core intellectual contribution of this paper. It means the stability properties of synchronization are fundamentally different and, in a way, better behaved than those of many kinetic plasma instabilities. We can actually use these amplitude expansion methods reliably, even in the low noise limit, which is often physically very relevant.
That contrast is a huge takeaway. Okay, does that feel like we've wrung everything out of sentence 4? The 0 noise limit, the finite coefficients, the Vlasov contrast?
I think so. It highlights a key technical result and its significance compared to related fields. Let's move on.
Sentence 5 introduces a specific scenario where the complexity really ramps up. For a bimodal reflection symmetric distribution, both types of bifurcation are possible, and they coincide at a codimension 2 Takens-Bogdanov point.
Right, so bimodal distribution. This just means the frequency distribution has two distinct peaks, maybe centered at plus omega dollars and omega dollars. Think of it as having two subgroups of oscillators, each pulling with a different characteristic frequency, but still balanced overall because of the reflection symmetry.
Okay, two competing groups.
Exactly. And this richer structure allows both types of instabilities we talked about. The steady state, where a real eigenvalue crosses zero, and the Hopf, where a complex conjugate pair of eigenvalues crosses the imaginary axis, to potentially occur in the same system just by tuning parameters.
And sometimes they can happen at the same time.
Yes. When the conditions for both the steady-state bifurcation and the Hopf bifurcation are met simultaneously, they merge at what's called a codimension 2 bifurcation.
Codimension 2, meaning you need to carefully tune two independent system parameters, like maybe the overall coupling strength dollars and the separation between those two peaks, no dollars, to hit this very specific point.
Precisely. You have to satisfy two conditions at once. And that specific merger point, where the steady state and Hopf lines meet in the parameter space, has a special name, the Takens-Bogdanov point. It's known in dynamical systems theory as a highly degenerate, very complex critical point.
Why is understanding this point so important?
Because it acts like an organizing center for all the complex dynamics nearby. Whether synchronization emerges smoothly or explosively, whether you get steady states or persistent waves, all these behaviors are intricately connected and organized around this single highly degenerate point. It's a crossroads of different dynamic possibilities.
Okay, the Takens-Bogdanov point marks peak complexity. Does that cover sentence 5 adequately? Bimodal, both bifurcations possible, coinciding at this codimension 2 point.
I believe so. It sets up the most complex scenario the paper touches on. Let's go to sentences 6 and 7, which describe the resulting physical states and their stability.
Sentence 6. The steady state bifurcation may be supercritical or subcritical and produces a time-independent synchronized state. Sentence 7. The Hopf bifurcation produces both supercritical stable standing waves and supercritical unstable traveling waves. First, supercritical versus subcritical.
Right. Supercritical means the new state, the synchronized state, or the wave, is stable and emerges smoothly or gracefully as you increase the critical parameter, like the coupling dollars. Its amplitude grows continuously from zero. Subcritical means the new state is actually unstable right at the bifurcation point. It often appears abruptly below the critical dollars and can lead to things like hysteresis, where the system jumps between states, or hard, explosive transitions.
Okay, so supercritical is smooth and stable, subcritical is abrupt and potentially unstable. Now, the Hopf bifurcation outputs two distinct wave types.
Yes, and this is crucial. The analysis predicts two kinds of time-periodic states emerging from the Hopf bifurcation in this O2 symmetric system. First, stable standing waves, SW. You can picture these as two synchronized clumps of oscillators, oscillating perhaps out of phase with each other, but remaining essentially fixed in their relative positions in phase space.
Okay, oscillating clumps, but stationary overall.
Exactly. And second, unstable traveling waves, TW. This corresponds more to a single synchronized clump that circulates continuously around the phase circle.
And the key finding here is the stability difference. SW are stable, TW are unstable.
That's the prediction from Crawford's analysis, yes. And the stability difference leads us directly to the correction of previous work, which is detailed in sentences 8 and 9.
Right. Sentence 8. Previous work on the Hopf bifurcation in a bimodal population by Bonilla, New, and Spigler, and Okuda and Kuramoto predicted stable traveling waves and stable standing waves, respectively. Sentence 9. A comparison to these previous calculations shows that the prediction of stable traveling waves results from a failure to include all unstable modes.
This is really the narrative engine driving the paper.
Yeah.
Crawford is essentially saying, look, this previous work by Bonilla, New, and Spigler, BNS, got the stability of the traveling wave wrong.
And why were they wrong? Does it link back to that symmetry argument?
Absolutely. It links directly back to the O2 symmetry we discussed. Remember that symmetry mandates that the complex eigenvalue driving the Hopf instability must be multiplicity 2. It has two independent eigenvectors associated with it.
Yeah.
BNS, in their analysis, effectively only included one of these eigenvectors. They missed the second one, the one related by the reflection symmetry.
So by neglecting that second mode mandated by the symmetry,
their mathematical model was incomplete. It fundamentally truncated the dynamics on the center manifold. This omission led them to an incorrect stability calculation, which erroneously predicted that the traveling wave, TW, was stable. Crawford's more complete analysis respecting the O2 symmetry fully shows that this TW is actually unstable, and the standing wave, SW, is the stable outcome.
Wow, okay, so the power of rigorously applying mathematical symmetry directly corrects a physical prediction about which collective state is actually observed. That feels like the central punchline of the abstract.
It really is. The final sentence just lists the keywords: oscillators, bifurcation, symmetry.
All right, have we thoroughly dissected the abstract now? We covered the model, the methods, the Vlasov contrast, the Takens-Bogdanov point, the wave types, and, crucially, the correction regarding TW stability due to O2 symmetry. Any critical rhetorical purpose missed?
No, I think we've got it. The abstract functions perfectly as a comprehensive summary, setting up the key results and the core intellectual contribution, particularly correcting that prior work. We're ready to move into the paper proper, starting with the introduction.
Okay, Section 1, Paragraph 1.1. This sets the historical context, mentioning pioneers like Winfrey and Kuramoto, and introduces the foundational microscopic model for the phase dynamics, which is given as Formula 1.
Right, this is the famous Kuramoto model. The formula is dou dash omega plus k fray 1 tie plus k fray for 1 n sub k theta dot sub I equals omega sub I plus k over n times the sum from j equals 1 to n of theta sub j minus theta sub I plus mi sub I of t. Let's break it down.
Okay. Pamita is the rate of change of phase for oscillator dollars.
Correct. Mega dollar is its natural intrinsic frequency, how fast it would spin on its own. The summation term is the crucial coupling term. A dollar is the coupling strength, how strongly they influence each other. It's scaled by a dollar similarly for mean field interaction. The interaction itself is mediated by the sign of the phase difference. Vitage theta, that specific sign function form is key.
And the last term?
That's a noise term, representing random fluctuations or external influences. Sakaguchi added this later. The amazing thing is how much complex collective behavior emerges from this relatively simple-looking equation, largely thanks to that sign coupling.
Okay, that's the microscopic starting point. Does that cover paragraph 1.1 and Formula 1?
I think so. It establishes the fundamental equation governing the individual oscillators. Let's move to paragraph 1.2.
Paragraph 1.2 introduces the way we measure synchronization, the macroscopic order parameter, written as radius and defined in Formula 2.
Yeah, this is the complex order parameter. The formula is RTE sum J1n RCT times e to the IPI of t equals 1 over n times the sum from j equals 1 to n of e to the I theta sub j of t. Think of each ei as a vector on the unit circle representing the phase of oscillator gi. This formula is just the vector average of all those individual phase vectors.
So RT is the length of that average vector.
Exactly. R measures the degree of coherence or synchronization. If all phases are random, the vectors cancel out, and one upperst dollars. If they all align, one uplight one. Synchronization onset happens when Forensite's going significantly above 0. For dt is the angle of that average vector, representing the average phase of the synchronized group.
Got it. $2 measures how synchronized, $2 measures where they're synchronized. Now, Formula 3 gives Kuramoto's famous result for the critical coupling strength, Kc, needed for synchronization to start without noise.
That's right. Formula 3 is AK2 D0 K sub C equals 2 over pi times G of 0. This assumes a unimodal symmetric frequency distribution, G beta, and crucially, no noise. G days is the density of oscillators with frequencies exactly at the center. Mean frequency assumes 0 here.
So the higher the density of oscillators near the center frequency, the smaller HAT needs to be. It's easier to synchronize them if they're already close in frequency.
Precisely. The threshold for instability, KCPA-DO, is inversely proportional to how peaked the frequency distribution is at its center.
Okay, we've covered the first 3 paragraphs now. The microscopic model, EQ1, the microscopic order parameter, EQ2, and the noise-free critical coupling, EQ3. Have we captured the essence of that initial setup?
Yes, I think we have. The groundwork is laid. The next logical step, as the paper takes in paragraph 1.3, is moving from these non-dollar individual equations to a description of the continuous distribution, which means bringing in the Fokker-Planck framework, especially when noise is present.
Right. Paragraph 1.3 mentions the subtlety of stability and introduces the Fokker-Planck equation, following Sakaguchi, for the large dollar limit. This is Formula 4.
Okay, Formula 4 is frac partial t to rho to frac partial t the partial derivative of rho a with respect to t, plus the partial derivative of rho times v with respect to theta equals d times the second partial derivative of rho with respect to theta squared. This is the core equation for the density.
Let's break that down. It looks like a conservation equation.
It is, fundamentally. The first term, partial p, is the rate of change of the density at a point in phase space. The second term, partial theta, is the divergence of the probability flux, how the density changes due to the deterministic flow velocity dollars. If these were the only terms, it would just be the continuity equation saying oscillators are conserved.
But there's the term on the right.
Exactly. The term total partial theta 2 is a diffusion term. It accounts for the effect of random noise, $ is the diffusion coefficient, related to noise strength, which tends to spread the distribution out. So it's conservation plus drift due to the d dollars plus diffusion.
Okay, that's the master equation for the density dollars. Does that cover Formula 4 and its meaning?
I think so. It describes the evolution of the statistical distribution. Let's move to paragraph 1.4, which clarifies what total actually represents.
Paragraph 1.4 defines Wonergio d theta. D theta gives the number of oscillators within a small range of phase theta and frequency omega, and it gives Formula 5 the normalization condition.
Right. Formula 5 is d theta omega 1. The integral from 0 to 2 pi of d theta, of theta omega t equals 1. This is crucial. It says that for any given natural frequency omega, if you integrate the density tall over all possible phases of theta from 2 to totua, you must get 1.
Meaning 100% of the oscillators at that frequency have to be somewhere in the phase circle.
Exactly. It's a probability density normalization for each frequency subpopulation.
Okay, normalization confirmed. Is paragraph 1.4 fully grasped?
Yes, definition of Turnus and its normalization. Let's proceed.
Paragraphs 1.5 and 1.6 show how the phase velocity from EQ1 and the order parameter from EQ2 are now rewritten using this continuous density torus. We get Formula 7 for the velocity dollars.
Formula 7 is VSI theta plus KR, the RRT, Siketa theta omega t equals omega plus KRT sinus sine of sigma minus theta. This is essentially the deterministic part of the original Kuramoto equation, EQ1, but now the coupling term depends on the macroscopic order parameters, Pletusly and TSET, which are themselves calculated from the density.
Self-consistent.
Yeah.
And Formula 8 gives the order parameter EI psi in terms of 2 or minus.
Yes. Formula 8 is arrow theta, EI theta, arrow t times e to the h e I e equals the integral from 0 to p of d theta times the integral from minus infinity to infinity of d omega of rho of theta omega t times d omega times e to the I theta. This is the direct continuum analog of the sum in equation 2. It's averaging EI theta over the entire population distribution BR.
Okay, so we've connected the microscopic velocity and macroscopic order parameter to the continuous density arrow. Do paragraphs 1.5 and 1.6 seem clear now?
I think so. It shows how the mean field coupling works in the continuum limit. Next is paragraph 1.7, defining the noise properly.
Paragraph 1.7 discusses the Gaussian noise terms 6t and I, and how they determine the diffusion coefficient dollars in the Fokker-Planck equation 4. The key statistical property is given in Formula 10.
Right, Formula 10 is critical. Like Coulat's 2D delta, the expectation value of C sub I of S times E sim J of T equals 2D times delta sub I times delta of S minus T. Let's unpack the pieces.
Okay. The angle brackets Langle dollar means statistical average. Geta C is the noise for oscillator at times past to sus.
Correct. The term delta is the Kronecker delta. It's one with no dollar and no these dual sev. This means the noise is uncorrelated between different oscillators. What happens to oscillator dollars is independent of oscillator jail.
Makes sense. And the delta, that's the Dirac delta function.
Yes, it's infinite $70 and zero otherwise, with unit integral. This means the noise is white noise. It's instantaneous in time, with no memory or correlation between different time points. What happens at time doesn't depend on what happened just before.
And the factor $2.
That $2 is the crucial link. It defines the strength or variance of this microscopic white noise, and it's precisely this dollar that appears as the diffusion coefficient in the Fokker-Planck equation. This formula provides the rigorous connection between the microscopic random kicks and the macroscopic diffusion process.
Okay, so paragraph 1.7 in Formula 10 establish the statistical nature of the noise and connect it to dollars. Are we good with that?
Yes, crucial connection made. Now we move to the standard procedure for stability analysis, linearization, covered in paragraphs 1.8 and 1.9.
Right. Paragraph 1.8 introduces the deviation either from the uniform incoherent distribution, either from the free.
Right, this lets us rewrite the Fokker-Planck equation in terms of this small deviation data leading to Formula 11.
Formula 11 is the core equation for the stability analysis. For partial eta plus n eta, the partial derivative of eta with respect to t equals n eta plus n of eta. This separates the evolution of the deviation eta into a linear part and a nonlinear part. And this structure is standard for bifurcation analysis, right?
Absolutely. The linear operator little dollar determines the stability of the incoherent state. Specifically, the eigenvalues of little tell us if small deviations littler will grow instability or decay stability. The nonlinear term make it becomes important after an instability occurs. It dictates how the growing deviation saturates and what the new synchronized state looks like.
Okay, so we need to look closely at the linear operator dollars. Its definition is given in Formula 12. This looks complicated.
It is non-trivial. Formula 12 defines leta inna, Leta eta b theta omega and kita plus first theta eg peta e keta plus cc aa theta and d theta plus cc theta eta defined as d times the second partial derivative of eta with respect to theta squared minus omega times the partial derivative of eta with respect to theta plus kot not over 2 times the quantity e to the minus I theta times the integral of d theta prime and d omega prime of eta ge to the a theta prime plus complex conjugate. Let's break it down into 3 parts.
First part, partial NA partial theta 2. That's the diffusion term, same as in Fokker-Klein.
Correct. Second part, omega partial eta partial theta. This represents the rotation or drift due to the natural frequency omega.
Okay. And the third part, the big integral term.
That's the linearized effect of the coupling term. Notice it involves Lyler, the coupling strength, and Redparin 5. Crucially, it includes an integral of Lane-Chi weighted by d'omega and ei theta. This integral is essentially calculating the first Fourier component of the deviation, which is related to the order parameter, to determine ei theta and its complex conjugate, the RDC20, then feed this average back to influence theta at phase theta. This is the non-local part. The behavior at theta depends on the average over all the theta.
So diffusion, rotation, and non-local coupling based on the average state. That's the linera. And Formula 13 defines the nonlinear term, lui2. We don't need the exact form now, but it depends quadratically on theta.
Yes. Meaning it involves terms like theta times derivatives of theta, or theta times the integral term. It's quadratic and higher order in theta. This term is negligible when theta is very small, hence linear stability is governed by Dahler, but it becomes crucial for determining the amplitude and stability of the synchronized state once eta grows larger after the bifurcation.
Okay, let's pause. We have introduced the full continuum equation for the deviation eta, broken into its linear dollar and nonlinear dollar parts, EQ 1113. Have we grasped the why of this structure? Why separate L and N?
Yes, I think we have. The structure lambda plus n is absolutely essential. The linear part tells us when the instability happens, the bifurcation point, where an eigenvalue of L crosses 0. The nonlinear part later tells us what happens after the instability. It saturates the growth and determines the properties of the new synchronized state. This separation is the foundation for the entire bifurcation analysis. We are now ready to tackle the symmetry aspect.
Right. Paragraph 1.10 discusses the crucial O2 symmetry. This symmetry arises if the frequency distribution is reflection symmetric, EQ 18. The symmetry operations themselves are given in formulas 15 and 16.
Okay, formula 15 is rotation. Theta plus theta plus phi omega, theta plus theta omega equals theta plus phi omega. This just means shifting all phases by an angle leaves the physics unchanged. Formula 16 is reflection. Theta omega equals minus theta minus omega. This operation simultaneously reverses the phase direction and the sign of the natural frequency.
And the condition for the system to have this full O2 symmetry, both rotation and reflection, is given in Formula 18.
Exactly. Formula 18 is G omega class of omega equals G of minus omega. The distribution of natural frequencies must be an even function, symmetric around 0. If this holds, the underlying equations respect both rotations and reflections. As we saw in the abstract, this symmetry has profound consequences for the types of solutions and their stability.
Paragraphs 1.11 and 1.12 then mention some subtleties. Even if the mean frequency isn't 0, we can sometimes shift to a rotating frame to recover the symmetry. And if reflectional symmetry, EQ 18, is broken, the symmetry reduces just to SO2 rotations only.
Correct. These paragraphs just handle those slightly more general cases. The core analysis really focuses on the O2 symmetric case defined by G omega.
Okay, does that cover the symmetry discussion adequately, the operations and the condition?
I think so. We understand what O2 means here and when it applies. Let's move to paragraph 1.13, summarizing the linear stability results.
Paragraph 1.13 references Strogatz and Marolo's work on the linear stability governed by do dollars. It mentions the continuous spectrum of dollars. What's that?
The continuous spectrum is basically a range of eigenvalues where the operator doesn't have nice isolated eigenfunctions. For this system, it lies along the vertical line X3 lambda. This means most general perturbations, which are composed of modes from this continuous spectrum, will decay exponentially with a rate determined by the noise dollars. It's like a background sea of stable, damped modes. This decay mechanism is sometimes called phase mixing, analogous to Landau damping in plasmas.
So the system is inherently stable for most disturbances. How does instability happen then?
Instability only happens if a discrete eigenvalue lambda emerges from this continuous spectrum and moves into the right half plane, meaning send Euler. This happens when the coupling dollar exceeds a critical value, Kc dollars. Below Kc dollar, all eigenvalues, discrete and continuous, are in the left half plane, so the incoherent state is stable. Above Kc dollar, at least one eigenvalue becomes positive, signaling exponential growth of a specific mode, the onset of synchronization.
And the formula for this critical coupling dollars in the presence of noise dollar is given in Formula 21.
Yes. Formula 21 is del C L meter CD plus omega 2 on K sub C equals the inverse of the integral from minus infinity to infinity of dg of omega over d squared plus omega squared. This is the generalized critical coupling found by Sakaguchi.
How does it relate to the simpler Kuramoto result, EQ3?
It reduces exactly to Kuramoto's del C's equals 2, the limit where the noise dollars goes to 0. So it's the correct generalization for the noisy case. Noise generally makes synchronization harder. It increases Kc dollars.
Okay, so paragraph 1.13 covers the continuous spectrum, phase mixing stability, and the noise-dependent critical coupling Kc 21 drill. Are we clear on the linear stability picture?
Yes, the basics are there. Stable below Kc 2, unstable above, with instability driven by a discrete eigenvalue emerging from the continuous spectrum. Now, paragraphs 1.13 and 1.14 bring us back to the context of previous work.
Right. Paragraph 1.14 discusses Bonilla et al., BNS, again. They looked at bimodal distributions and found Hopf bifurcations, but as mentioned in the abstract, Crawford states they failed to include both unstable eigenvectors required by the O2 degeneracy.
Exactly. It reiterates the core criticism based on symmetry.
Paragraph 1.15 then discusses Okuda and Kuramoto. They studied a system of two coupled subpopulations, which Crawford notes as a special case of the general Fokker-Planck model here. What did OK find?
Interestingly, OK did find both traveling wave and standing wave solutions, and their analysis suggested the standing waves were stable, which aligns with Crawford's eventual conclusion. However, Crawford notes they didn't explicitly discuss the underlying O2 symmetry or the reasons for the eigenvalue degeneracy. So their result was correct for their specific model, but lacked the general theoretical framework and explanation based on symmetry that Crawford provides.
So BNS missed a mode due to symmetry. OK found the right stability in a special case, but without the general symmetry argument. Crawford is aiming to provide the complete symmetry-based picture.
That's the narrative, yes. Paragraph 1.16 and it just outlines the structure of the rest of the paper. Section 2 will delve into the linear theory and the spectrum, including the Takens-Bogdanov point, and Section 3 will derive the amplitude equations using center manifold reduction.
And paragraph 1.1c wraps up the introduction by re-emphasizing two key points. First, the contrast with loss of instabilities, the coefficients here remain finite as $0 to $.
Crucial difference in mathematical structure.
Second, it previews the main results for the bimodal population using O2 theory. The steady state can be super or subcritical, and the Hopf bifurcation yields supercritical stable standing waves, SW, and supercritical unstable traveling waves, TW.
Setting up the expected conclusion based on the symmetry arguments.
Okay, that's the end of the introduction. We've set up the Kuramoto-Fokker-Planck framework, defined the order parameter, discussed the critical coupling, highlighted the crucial O2 symmetry constraints, summarized the linear stability picture, and clearly stated the paper's mission to correct prior work, especially BNS, on Hopf stability using this O2 framework. Have we missed any important details or context from Section 1 before we dive into the spectrum analysis in Section 2?
No, I think we've thoroughly unpacked it. We understand the model, the key players, Matisse-on zeros, the importance of symmetry, and the scientific problem being addressed. We have the necessary context for the deep dive into the linear operator and its eigenvalues, which is coming up next.
All right, Section 2, linear theory. This is where the detailed mathematical analysis of the operator dollar happens. Paragraph 2.1 starts by using Fourier expansion because the phase theta is periodic. Formula 22 shows the expansion.
Yes, since theta is 2 pi periodic and theta, we can write it as a Fourier series. Formula 22 is the omega eta beta, eta of theta omega equals the sum from L equals minus infinity to infinity of eta sub L of omega times e to the IL theta. Here, theta omega are the complex Fourier coefficients, which still depend on the frequency ego.
And applying the linear operator dollar to this expansion gives Formula 23.
Right. Eta URL eta equals the sum from L equals minus infinity to infinity of L sub L eta sub L times e to the IL theta. This shows that dollar acts independently on each Fourier mode via a simpler operator.
Okay, so the action of dollar decomposes by Fourier mode. What is the explicit form of dollars given in Formula 24?
Formula 24 is dollar or omega il mis dollar il It'll whale, atol catala, it'll plus tierpo k tilde 1 plus tilde y she, it'll like to L sub L eta sub L equals minus IL times the quantity omega minus ILD times ota sub L plus pi rho naught k times the quantity delta sub L comma 1 plus delta sub L comma minus 1 times the integral of d omega g of omega pi eta sub L of omega prime.
Let's break that down. The first term, omega ILD, looks like it comes from the rotation and diffusion parts of dollar.
Exactly. The ill omega term comes from the rotation dollar omega partial theta, and the L nego elevated dollar term comes from the diffusion little partial theta detail after Fourier transforming. So this part is local into omega.
But the second term, the one with the integral, that's the coupling. And it has those Kronecker deltas, delta M11, antal S, 1 defil 12th, 1 del. What do they do?
They are crucial. They are 0 unless exactly 1 or -1. This means the non-local coupling term, the integral over all frequencies to omega, only appears in the equations for the Lund dollar 4 and 5 modes. For all other modes, PM2, TM3, this coupling term vanishes.
So the collective interaction only directly affects the first Fourier harmonics. This explains why the instability is associated with these modes.
Precisely. Also, Formula 25 notes ET equiv 1, why is the AL dollar 4 0?
That must come from the normalization condition, Formula 5-14. Integrating eta over theta must give 0 because both 2 eta and over dollars integrate to 1. The integral of theta over theta is just 2EB a times the low Fourier coefficient theta dollars, so 2E this be 0.
Exactly right. Conservation of oscillators means the average density deviation is 0.
Okay, paragraph 2.1. Fourier expansion simplifies Lawler into dollars, and crucially, the coupling only acts on 1 theta Law. Does that seem complete?
Yes, that sets up the structure for the eigenvalue problem. Paragraph 2.2 then introduces the mathematical tools needed for projections later. The inner product and the adjoint operator.
Right. Formula 26 defines the inner product for functions depending on the theta and omega. And formulas 27, 28 define the adjoint operator. Later, Dogger, why do we need the adjoint?
It's a standard technique, especially in infinite dimensional spaces like this one, functions of the omega. When we find the critical eigenvectors of liter dollar, let's call one drun, associated with an instability, the center manifold reduction requires us to project the current state L dollar onto that eigenvector. This projection isn't just taking a simple dot product. It requires using the corresponding eigenvector of the adjoint operator, let's call it L dagger. The projection amplitude is then given by the inner product, using the definition from 26.
Okay, so Later Dagger and its eigenvectors are needed to properly calculate the amplitudes on the center manifold. Have we missed the strategic goal of introducing the adjoint here?
No, I think that captures it. The adjoint Later-Daggers is essential because its eigenvectors phi dagger form the basis for projection in this function space via the inner product. This setup is absolutely foundational for deriving the amplitude equations later. Let's move on to the eigenvalue problem itself.
Paragraphs 2.3 and 2.4 set up the eigenvalue problem lambda p, looking for solutions where keta grows or oscillates persistently, i.e. text kate. They use a scaling lambda p for convenience, leading to formula 33.
Right. The scaling is just a mathematical convenience often used in kinetic theory. The key result stated here is profound. Non-singular eigenfunctions, representing discrete eigenvalues lambda, exist only if lambda.
Why only lambda dollar?
Because for Nick and Dia, the operator from EQ24 simplifies to just L omega L2D. The eigenvalue problem becomes L omega LTD, L omega L2D. The only solutions correspond to lambda L omega L2D, which has real part equal to the lambda Dia. Since Nick and dollars, this is always negative for D dollars. These eigenvalues form the continuous spectrum we talked about earlier. They're all damped modes, independent of the coupling dollars or the frequency distribution omega. Only for $2, where the coupling term is present, can we get eigenvalues lambda that might cross into the right half plane as dollars increases.
So the possibility of instability is entirely confined to the lambda and de-lambda Delaurent subspace because that's where the collective coupling term lives.
Makes sense.
Exactly. Paragraph 2.5 then focuses on these lambda to 1 modes. It states that if we look for non-singular solutions, eigenfunctions, they must satisfy a constraint involving a quantity store related to the eigenvalue lambda by lambda, dol. This dol must be a root of the spectral function lambda. This function is defined in formula 37. Okay, formula 37 is lambda z equiv 1 plus il frax gil lambda sub il z defined as 1 plus ilk over 2 times the integral of d omega prime g of omega prime over omega prime minus z minus ild. This looks like the core of the eigenvalue condition.
It is. The roots d dollars of this complex equation, lambdols, determine the discrete eigenvalues lambdol of the linear operator dollar. These are the eigenvalues that can potentially emerge from the continuous spectrum and drive the instability. synchronization. Finding the roots of Lambda is equivalent to solving the linear stability problem.
Okay, the roots of Lambda give the critical eigenvalues. Does that wrap up paragraph 2.5?
Yes, definition of the spectral function. Paragraph 2.6 then explores crucial symmetry properties of this function.
Right. Formula 38 gives an identity lambda z. What does that imply?
It ensures that if lambda under Ilsbils is an eigenvalue, meaning lambda, then its complex conjugate, a lambda, is also an eigenvalue because it corresponds to lambda Ilsbils. Eigenvalues must come in conjugate pairs if they are complex. This is always true.
Okay, standard result. But Formula 39 only holds if O2 symmetry applies. Omega is even. It states lambda. Lambda, what's the significance of this one?
This is the O2 guarantee. If Zadels is a root, so lambda, then this identity implies lambda Ilzil. So if Zils is a root, then Zil is also a root for the same dollars. Now, is Delos is purely imaginary, then Zildis is Iwi, so it doesn't give a new root. But if Zellers has a non-zero real part, Zellers is x plus I with 6 Iwid, then Zoli Zel equals x Iwis plus Iwi. This is a distinct root from Zildil.
So if the eigenvalue lambda ixilsmuf oven or is complex, which happens if Zido has a non-zero real part, the O2 symmetry guarantees there's another distinct root, $z$ equals zgi O, corresponding to the same value of ball. This means the complex eigenvalue lambda must have at least two independent modes associated with it. This is the source of the degeneracy.
Precisely. Relation 39 is the mathematical embodiment of the O2 symmetry acting on the spectrum. It forces complex eigenvalues, which lead to Hopf bifurcations, to be degenerate, having multiple eigenvectors. This is the exact point that Crawford argues BNS missed.
Okay, let's do a check here. We've defined the spectral function lambda zu, EQ37 fellers, whose roots give the eigenvalues. And we've seen how symmetry relations EQ38-39 dictate properties of these roots, especially the O2 symmetry EQ39, forcing degeneracy for complex eigenvalues. Have we fully captured the geometric interpretation and significance here?
I think we have. We see how the problem structure, symmetry via even Doega, translates directly into mathematical constraints on the eigenvalues, which forces the degeneracy crucial for the later stability analysis. Ready for the next step?
Yes. Paragraph 2.7 introduces more technical machinery. The projection operator lambda onto the generalized eigenspace lambda, defined via a contour integral involving the resolvent operator lambda LO1. This looks like setup for center manifold reduction.
It is exactly that. Formulas 4022 define these standard tools from operator theory. The goal is to have an explicit way to calculate the projection of the state onto the critical modes, those with lambda approx. Since we know eigenvalues only occur for Ley-Dollar, Formula 43 shows that this projection lambda simplifies significantly.
Formula 43 is lambda A level 1 plus lambda R1 plus fraganda I1 plus fraganda R. It only involves the Levon and Levum components, AO1 and their respective resolvents.
Correct. The projection onto the critical subspace only depends on the Lenormand-Fourier modes of the state, as expected from our earlier analysis of dollars. This machinery will be used explicitly later to derive the amplitude equations.
Okay, paragraph 2.7 sets up the projection operator needed later. Does that seem clear?
Yes. Technical but necessary setup. Now we move into subsection 2.1, which analyzes the case of simple roots and semi-simple eigenvalues.
Subsection 2.1 starts by defining a simple root zeta lambda as one where lambda is but the derivative lambda. This leads to simple or semi-simple eigenvalues. Semi-simple essentially means the geometric multiplicity, number of independent eigenvectors, equals the algebraic multiplicity, order of the root. No generalized eigenvectors are needed here.
Okay. First case, 2.1.1 real eigenvalues. This corresponds to a steady-state bifurcation. Here, z-dollars is purely imaginary, say ziddle, so lambda ln1 ziddles is real. What does O2 symmetry tell us here? Even for a real eigenvalue, O2 has consequences. It ensures there are two linearly independent eigenvectors. One is Ganta Spada, given in EQ46, involving EQ46. The other is its reflection, kappa psi, which turns out to be the complex conjugate EQ48 tound. So the eigenspace is two-dimensional, spanned by Trivenson psi.
And the paper explicitly constructs the corresponding adjoint eigenvectors kappa psi EQ49 to 52 and confirms they satisfy the necessary biorthogonality conditions, EQ43, 54.
Yes, this is careful bookkeeping to ensure the projection formula works correctly. The payoff is equation 56, which gives the explicit projection onto this 2D center manifold for the real eigenvalue case.
Formula 56. This confirms the projection is a sum of two terms, corresponding to the two eigenvectors Gansa-Skada. The amplitudes are the inner products with the adjoint eigenvectors.
It's exactly. This concerns that even for a simple real eigenvalue, the O2 symmetry forces a two-dimensional center manifold description. The dynamics near the steady-state bifurcation will be governed by the evolution of these two amplitudes, invalidated.
Okay, that covers the real eigenvalue steady-state case. Now for 2.1.2, complex eigenvalues corresponding to a Hopf bifurcation. Here, $$ is complex, z values x plus I with 60 is 2 squared 60 squared 0, 1. Why is this eigenvalue multiplicity 2?
This is the core point again. Because of the O2 symmetry relation lambda 0, 0, we know that if C0 is a root, then Z is also a root for the same $. These two roots, Zers and Zers, correspond to the same complex eigenvalue lambda and its conjugate lambdas. The eigenvector associated with VCCTs, 50, 70, the eigenvector associated with the distinct root in Zers is related to stetas by the reflection operation.
Yeah.
So the single complex eigenvalue lambda has two linearly independent eigenvectors and kappa state purely because of the O2 symmetry. Precisely. This is the critical degeneracy. The geometric multiplicity is 2. When you also consider the conjugate eigenvalue lambda, which has eigenvector CISA, the total center manifold for the Hopf bifurcation is 4-dimensional.
And this is the degeneracy BNS missed. They essentially only considered the space spanned by psi and ossize, neglecting the kappa kathas components required by symmetry.
That is exactly Crawford's argument. The projection onto the center manifold, plan idea, given in equation 60, again explicitly shows two terms involving the amplitudes and kappa theta, confirming the two-dimensional structure associated with the eigenvalue lambda itself, and another 2 for lambda.
Okay, let's verify this part. We've clarified that O2 symmetry mandates multiplicity 2 semi-simple eigenvalues for both real steady-state 2D center manifolds spanned by ISI, kappa clad dollars, and complex Hopf 4D center manifold spanned by ISI, and their conjugates, bifurcations. We trace the connection from the spectral function roots in symmetry relation 39 to this eigenvector multiplicity. Does this cover the semi-simple cases?
Yes, I think we firmly established that simple roots plus O2 symmetry dictate these specific eigenvector structures and manifold dimensions. Now we need to consider the case where the root is not simple.
Right, subsection 2.2, multiple roots and non-semi-simple eigenvalues. This happens when the eigenvalue condition lambda occurs at the same time as lambda. What does this imply physically?
This typically happens at special points in parameter space, where different types of bifurcations might meet or change character. Mathematically, it means the eigenvalue is non-semi-simple. The algebraic multiplicity, how many times $, is a root, is greater than the geometric multiplicity, number of true eigenvectors. To span the full critical subspace, we need not only eigenvectors upsilon, but also generalized eigenvectors upsilon.
Equation 62, 63. Define a generalized eigenvector upsilon via upsilon. It's like one step removed from a true eigenvector. The analysis shows, EQ 67, that such a solution upsilon only exists if lambda eigenvector is confirming it's tied to non-simple roots.
Correct. The focus here is specifically on the Takens-Bogdanov case. A real eigenvalue, so $8, which is non-semi-simple. This requires lambda $1, the steady-state bifurcation condition, and name lambda 1 up also.
Why is this case so important? We're mainly interested in the simple steady-state and Hopf bifurcations, aren't we?
We are interested in them, but the Takens-Bogdanov point is where the lines of steady-state bifurcations and Hopf bifurcations meet in the parameter space, like in figure 1. It's the point where the real eigenvalue lambda $, becomes non-semi-simple, just as the complex pair from the Hopf branch hits the real axis and merges with it. Understanding the structure at this merger point is crucial for understanding how the dynamics transition between the two types of bifurcations nearby.
Ah, okay. So understanding the non-semi-simple structure is key to understanding the transition region itself. The paper then explicitly constructs the eigenvector EQ $70 and the generalized eigenvector upsilon EQ 71, along with their reflected counterparts, kappa dot upsilon.
And similarly, it constructs the adjoint eigenvector EQ72 and generalized adjoint upsilon EQ73 and lists all the necessary biorthogonality relations, EQ74, 77, needed for projection.
The final result is the projection lambda eta for this non-semi-simple case, equation 84. It involves 4 terms projecting onto the space spanned by 8 psi kappa got psi upsilon kappa got epsilon. So the center manifold at the Takens-Bogdanov point is 4-dimensional.
Yes, spanned by 2 eigenvectors and 2 generalized eigenvectors, all required by the O2 symmetry and the non-semi-simple nature of the lambda eigenvalue at that specific point.
Okay, let's verify this subsection. We explored why we need generalized eigenvectors, upsilon for non-semi-simple eigenvalues, where lambda go. We focused on the Takens-Bogdanov point, real non-semi-simple lambda-dal, as the merger point of steady state and Hopf bifurcations. We noted the construction of psi upsilon and their adjoints, leading to a 4D center manifold projection, EQ84. Have we sufficiently justified the need for this detour into non-semi-simple theory?
I believe so. We've established its role as the organizing center for the transition between the two main bifurcation types. It's essential context for interpreting the parameter space diagrams later. Now, subsection 2.3 provides a concrete example.
Subsection 2.3, example of a bimodal population. This applies all the preceding theory to a specific frequency distribution, two Lorentzians centered at lambda PM omega with epsilon given in equation 85.
This is a classic choice because it's mathematically tractable and captures the essence of competing subpopulations. Calculating the spectral function lambda1 leads to an algebraic equation whose roots as semi-Bonilla can be found explicitly, EQ88.
And the nature of these roots, real or complex, depends on the parameters AP taller or epsilon, D taller. The analysis identifies the key parameter boundaries where things change.
Right. KKK where eigenvalues might disappear into the continuous spectrum. Take E teller Ida where a real eigenvalue crosses 0. Steady-state bifurcation condition given by EQ90.
Yeah.
KK4 omega, where the two roots collide on the real axis, potentially leading to the non-semi-simple case, where a complex conjugate pair crosses the imaginary axis, Hopf bifurcation condition from EQ91.
And crucially, the paper notes the codimension 2 point, where the steady-state line and the Hopf line meet. This occurs precisely when 154 epsilon plus D and omega to 2 epsilon plus D to come to 2. This is the Takens-Bogdanov point for this specific model.
Exactly. Figure 1 in the paper maps these boundaries in the omega to 2-day plane. It shows how, as you increase the separation omega dollars between the two peaks, the instability tends to switch from a steady-state type to a Hopf type.
The summary notes this leads to stable standing waves, as Kuramoto had hypothesized for such bimodal distributions.
Yes, this specific example sets the stage perfectly for the nonlinear analysis in Section 3, where the stability of these standing waves will be rigorously determined.
Okay, that completes Section 2, the linear theory. We've gone from Fourier modes to the spectral function, analyzed its roots under O2 symmetry, understood semi-simple, steady-state, Hopf, and non-semi-simple, Takens-Bogdanov eigenvalues, and seen how it plays out in the bimodal example, identifying the key bifurcation boundaries. Have we missed any critical details regarding the structure of the spectrum or the setup for the nonlinear analysis?
I think we've thoroughly unpacked it. We have a complete picture of the linear stability. The damped continuous spectrum provides the background, while discrete eigenvalues merging from it, governed by roots of lambda, drive the instabilities. We understand the crucial role of O2 in determining the degeneracy of these eigenvalues. We're fully prepared to tackle the nonlinear dynamics in Section 3.
All right, Section 3 gets into the heart of the matter, analyzing the dynamics after the instability sets in, using the center manifold reduction tools set up in Section 2. Paragraph 3.1 starts by looking at the nonlinear term eta and Fourier space, EQ95.
Right. The key thing about NADA is that it involves products of teloterms. In Fourier space, a product becomes a convolution. This means the nonlinear term couples different Fourier modes together. Specifically, it shows that the telo-Haven critical modes interact nonlinearly to generate higher harmonics, telo2, PM33, etc., and also feedback on themselves. This coupling is what saturates the exponential growth predicted by linear theory.
So non-OK mediates the energy transfer between modes. Does that cover paragraph 3.1?
Yes, it sets up how nonlinearity acts in Fourier space.
Now, subsection 3.1 focuses on the first case, the steady-state bifurcation, hashtag 3.1 steady-state bifurcation.
Here we're assuming a simple real eigenvalue lambda crosses 0 at quantA6 fixture. We know from Section 2 that the center manifold is two-dimensional, spanned by the eigenvector Zollard as reflection, conjugate KA6 20 and T. The state Yeatonerian criticality can be written as a combination of these modes plus stable modes. It's exactly. Equations 96 formalize this decomposition. The full state gatus is split into its projection onto the center manifold, lambda eta, which can be written in terms of complex amplitudes. Alpha, multiplying the eigenvectors, plus the remaining part 0, which lies in the stable subspace. The dynamics then decouple. Equation 99 gives ODEs for the slow amplitudes, alpha, on the center manifold, and equation 100 gives a PDE for the fast stable modes, ZR-dal.
The core idea of center manifold reduction is that the slow dynamics of alpha dictate the long-term behavior, right? We need to find the equation for alpha.
Correct. Subsection 3.1.1 focuses on these dynamics. The center manifold theorem says the stable modes are enslaved to the slow modes, meaning Zell can be written as a function all the amplitudes. Alpha, AQ103. Substituting this back into the equation for alpha gives the closed amplitude equation. Crucially, the O2 symmetry imposes strong constraints on the form of this equation. O2 symmetry dictates that the evolution equation must respect rotations and reflections. This forces the amplitude equation to take the specific form adicuro p sigma, EQ108, where sigma alpha 2 is the only rotationally invariant combination of alpha and alpha. P sigma is some complex function initially.
So the rate of change of alpha is proportional to alpha itself, times a factor that only depends on the magnitude squared, alpha 2, 2. Expanding this near alpha dollar gives the standard form in equation 109.
Precisely. Equation 109 is alpha lambda plus p sigma plus dos alpha dot equals alpha times the quantity lambda plus p sub sigma of 0 times magnitude alpha squared plus higher order terms. Here, lambda is the linear growth rate, proportional to L2. The coefficient sigma is the crucial cubic coefficient. Its real part determines the stability and direction of the bifurcation.
Okay, so the goal is to calculate this coefficient sigma. Subsection 3.1.2 tackles this. It seems to involve finding the function alpha that describes the stable modes.
Yes, specifically we need the quadratic terms in dollars. The nonlinear term in the original equation contains terms quadratic in the critical modes, like alpha 2. These quadratic terms act as a source or forcing term for the stable modes Zevel. The stable modes respond linearly to this forcing, resulting in several of the dollars being quadratically dependent on alpha and alpha. We need to calculate this response.
The calculation focuses on the opal2 component of dollars called H2 of dollars, YL2.
Because the quadratic nonlinearity involves terms like alpha psi plus alpha su 2. Since Joy contains alpha theta, the square will contain terms like alpha psi and al the other dollar. The LPN of the dollar contains delta theta. It turns out this opal2 response is critical for calculating the cubic term sigma back in the alpha equation.
Okay, so we need to solve for the 202 part of the stable manifold response to each dollar, which is done in equation 131. Plugging this back into the projection formulas yields the final expression for the cubic coefficient Talus sigma in equation 132.
Right. Equation 132 is a to the pi of 0, n to 1. Only need to make 0 I2d. P sub sigma of 0 equals minus pi squared k cubed over 2 times lambda prime sub 1 of 0 times the integral from minus infinity to infinity of d omega g of omega over omega minus 0 minus id squared times omega minus 0 minus I2d. This looks complicated, but it's an explicit formula. The O2 symmetry guarantees that even though the integrand is complex, the final result for PCO bog must be real.
Okay, we have a formula for the cubic coefficient. Does that cover subsection 3.1.2?
Yes, the derivation of sigma now 3.1.3 applies it to the bimodal example.
Subsection 3.1.3 evaluates formula 132 for the 2 Lorentzian distribution, EQ85, along the steady-state bifurcation curve, KKC. The result, EQ133, gives sigma 0 logs in terms of the model parameters, AKC, epsilon, d, omega do. What does the sign tell us?
The sign of sigma determines the bifurcation type. The calculation shows the sign depends on the term omega 2, omega 2, 2, where omega is related to diodo as napson. If comega omega peaks are close together, sigma is negative, peaks are far apart, sigma is positive.
And what does negative versus positive sigma mean for stability?
If sigma, the cubic term stabilizes the growth. This corresponds to a supercritical bifurcation. The synchronized state emerges smoothly for co-phi2u and is stable. If sigma, the cubic term is destabilizing. This is a subcritical bifurcation. The synchronized state that emerges is unstable, and the transition is likely to be abrupt or hysteretic.
So just by changing the separation megadol of the peaks in the frequency distribution, the nature of the synchronization onset changes from smooth and stable to abrupt and unstable.
Exactly. The shape of omega dictates the outcome.
Okay, that covers the bimodal example result. Now, subsection 3.1.4 looks at the dollar-to-dollar limit again.
Right, the zero noise limit. This revisits the Vlasov contrast. As dollars to dollars, the denominators in the integral for sigma d EQ132 approach the real axis, causing singularities. If this was Vlasov-Poisson, the coefficient would typically diverge.
But here,
Crawford shows using complex analysis techniques, Plemish formulas, analytic continuation, that these singularities effectively cancel out or can be handled properly, resulting in a finite value for sigma, even as dillar to dollars. The result is given approximately in equation 139.
Equation 139, $50 0 0 0 do O fashion 2 $0.
Equation delivered today, 0. For typical smooth unimodal-like distributions, the second derivative is negative and the integral term is positive, making sigma negative overall.
Yes. This predicts that for many reasonable frequency distributions, the steady-state bifurcation should be supercritical in the low noise limit. This confirms the robustness of the analysis compared to Vlasov. Okay, the Vlasov contrast holds for the nonlinear coefficient too. Finally, 3.1.5 briefly mentions perturbing the symmetry. If we break reflection symmetry, moving from O2 to just SO2,
then the real eigenvalue, lambda dollar, typically splits into a complex conjugate pair near the imaginary axis. The steady-state bifurcation is destroyed and replaced by a Hopf bifurcation, leading to traveling waves instead of a stationary synchronized state. Symmetry breaking drastically changes the outcome.
Okay, let's do a check on the steady-state section, 3.1. We derived the amplitude equation, EQ109, focused on the cubic coefficient sigma, calculated at EQ132, saw how its sign determines supersubcriticality in the bimodal example based on omega dollars, confirmed finiteness is liter to dollar, it's less soft contrast, and noted how breaking symmetry leads to waves. Have we missed any key connections or implications?
No, I think we've thoroughly unpacked the steady-state bifurcation. We understand its description via sigma and its dependence on Biga and, importantly, its well-behaved nature in the low noise limit. The next logical step is applying the same center manifold machinery to the complex eigenvalue case, the Hopf bifurcation.
Right, subsection 3.2. Hopf bifurcation. This is where the main correction happens. Hashtag tag 3.2 Hopf bifurcation.
We're now near Kamor, where a simple, complex eigenvalue lambda compifable crosses the imaginary axis. As established rigorously in section 2, due to O2 symmetry, this eigenvalue is multiplicity 2. The center manifold is four-dimensional.
Spanned by the eigenvector psi, kappa phi eigenvalue lambda, and their conjugate psi for eigenvalue lambda. We need amplitudes for both eights and kappa phi. Let's call them alpha and beta phi. Exactly. Alpha t approx. Alpha t is the amplitude of the mode related by reflection, the one BNS neglected. Equations 141, 48 set up the decomposition into these critical modes, alpha, beta, and the stable transverse modes, dollar. Section 3.2.1 focuses on the dynamics on this 4D center manifold. Again, the stable modes, psi dollars, are assumed to be a function dollar of the amplitudes, EQ 149. This leads to coupled amplitude equations for alpha and alpha dollars, EQ 150, 151. How does O2 symmetry constrain these?
The symmetry operations act on the amplitudes. Rotation by alpha data transforms them as alpha, beta alpha. E alpha data, alpha beta equals e to the minus I phi alpha, e to the I phi beta. Reflection swaps them. Kappa na beta alpha, kappa alpha beta equals beta.
These transformations, plus an additional phase shift symmetry inherent in the problem, severely restrict the form of the cubic terms in the amplitude equations. After removing some terms via coordinate changes, normal form theory, the system reduces to the standard O2 Hopf normal form, equation 165.
Right. The dynamics depend only on two real invariant quantities. $1 plus beta 202 total intensity, and delta beta 2 alpha 2 difference in intensity between the reflected modes.
This leads to simplified amplitude equations for the real magnitudes 6 beta dollar and 6 beta dollar is 6 beta beta, given in equations 168, 169, and 10. These equations are governed by just two crucial real cubic coefficients called PAMA by $1, plus PY1 12, plus PB0 by 12, plus PO0 by 12, plus PO0 by 12. The fate of the system which wave pattern emerges and whether it's stable depends entirely on the signs and relative magnitudes of $2 and 2.
And this two-dimensional system predicts two main types of solutions, summarized in Table 1. Yes. First, traveling waves, TW. These correspond to solutions where one amplitude is 0, either 6TW or $2 XTW. Only one of the rotational modes, alpha or beta, is excited. Physically, this is the single circulating clump.
Second, standing waves, SW. These occur when both amplitudes are equal and non-zero, SXSW, XSW. Both the original mode and its reflection are equally excited. Physically, this is the two counter-propagating clumps. The frequency of oscillation omega near criticality is given by equation 170. Okay, so the O2 normal form naturally predicts both TW and SW solutions. Their existence and stability depend on one uncertain. Subsection 3.2.2 explains how to calculate these coefficients.
Similar to the steady-state case, it involves calculating the quadratic response dollar at the stable modes to the forcing from the critical modes. Here, because we have alpha and beta, the quadratic forcing is more complex, EQ 179, and we need to calculate 3 different components of the delta-2 response, denoted as Suchidana 1, Torchidana 1, 0, 1, and 5, but
Once these are found, equations 177, 178 give the final expressions for Pew dealer and $3 in terms of integrals involving these 22 components and the eigenvector subjoints. And crucially, the paper reemphasizes the Vlasov contrast.
yes, it confirms that, unlike in Vlasov theory, where Hopf coefficients often diverge, like d3 are expected to remain finite as Dale to dollars. This means stable oscillations are predicted even in the absence of noise, a key physical difference.
Okay, we have the formulas for Pew dollars. Let's see what happens in the bimodal example, subsection 3.2.3.
Applying these formulas to the 2 Lorentzian population at the Hopf boundary Corkera, Crawford determines the signs of the coefficients. By inspection of the integrals involved, it's argued that the real parts of the terms contributing to Pew and Puer have specific signs. Text wrangle Langle and text wrangle down found to be positive.
What does this positivity imply for Pew dollar and $3?
It leads to the conclusion that Pew must be negative. This means the Hopf bifurcation itself is supercritical. The amplitude of oscillations grows smoothly from 0. More importantly, the analysis shows that the coefficient $, which involves the term P, epsilon, d omega 2 no, EQ 192, is always positive, because P is positive.
Okay, so the crucial result for the bimodal example is Pew dollars and $3 the Zeller. What does this combination predict for the stability of the waves?
Let's check the stability conditions from the normal form analysis, often shown in diagrams like Figure 2. For standing waves, where 60 in parts are up to $2 CO, since Pew dollars and R2, both conditions are met. Therefore, standing waves are supercritical and stable.
And for traveling waves, where one amplitude is $6, the other is 0.
Stability requires Pew H dollars, which is true, and the Allers Lars, but we found over college is positive. Therefore, the second condition fails. Traveling waves are supercritical but unstable.
There it is. The rigorous calculation confirms the stability. SW are stable, TW are unstable. This directly contradicts the BNS prediction of stable TW.
Precisely. Subsection 3.2.4 drives this point home. It compares the full amplitude equations, 168, 169, with the truncated system, 194, that BNS effectively analyzed by setting beta dollars 1, or 6 by 2 dollars. The BNS system only has the TW solution, and its stability only depends on Pew dollars, which is negative, leading them to incorrectly conclude the TW is stable. They missed the destabilizing influence captured by the positive Crew coefficient, which only appears when considering the interaction between the alpha and beta Kara modes mandated by O2.
A clear resolution based on including the full symmetry. Subsection 3.2.5 then compares with Okuda and Kuramoto.
Okay, it shows that the OK2 population model is mathematically equivalent to the bimodal Lorentzian case here, when the Lorentzian with epsilon 2 delta function distributions. OK's simulation results, which found stable standing waves, are therefore fully consistent with Crawford's general O2 analysis.
And finally, 3.2.6 notes what happens if O2 is perturbed down to SO2 by breaking reflection symmetry.
The multiplicity 2 complex eigenvalue splits into 2 distinct complex conjugate pairs. This typically leads to 2 separate Hopf bifurcations, and the standing waves perturb into more complex modulated wave patterns.
Okay, let's verify section 3. We meticulously derived the amplitude equations for both steady-state and Hopf bifurcations using center manifold reduction under O2 symmetry. We confirmed finiteness as $0 a dollars. For the bimodal example, we found the steady-state can be super or subcritical, while the Hopf always leads to stable standing waves and unstable traveling waves. We explicitly showed how this corrects the BNS result by including the reflection mode. Have we secured the main finding regarding the stability correction and the role of O2?
Yes, I think we've thoroughly unpacked it. The correction proving stable SW and unstable TW coexist due to O2 degeneracy, resolving the BNS discrepancy, is the absolute central takeaway of the nonlinear analysis in Section 3.
Moving now to the final discussion in Section 4. Paragraph 4.1 summarizes the findings, referencing Figure 4, which maps out the regions of different stable states in the parameter space. Incoherent, partially synchronized from the steady-state bifurcation, and standing waves from the Hopf. It notes a gap in the analysis, though.
Right. The paper has analyzed the bifurcations from the incoherent state. It hasn't analyzed the transitions between the partially synchronized state and the standing wave state, represented by the dashed line in Figure 4. More significantly, it highlights the challenge of analyzing the dynamics right at the O2, taking Bogdanov point itself the merger point.
Why is that point so challenging?
Because it's highly degenerate. We saw in Section 2 it involves a non-semi-simple eigenvalue. Furthermore, in the bimodal example, the steady-state bifurcation becomes subcritical near this point. Standard Takens-Bogdanov normal form theory usually assumes supercriticality. Handling the O2 symmetry combined with this non-semi-simple eigenvalue and the subcriticality requires extending existing normal form theories. Crawford suggests it might even involve higher-order degeneracies, potentially requiring analysis near a codimension 3 bifurcation point to fully capture the behavior.
Wow, so the complexity really escalates dramatically right at that intersection point. It remains an open challenge for future work.
Exactly. The dynamics there are expected to be very rich and complicated.
Okay, have we covered the key points of the discussion? Summary of stable states found, identification of the Takens-Bogdanov point as the major challenge requiring more advanced theory.
I think we've thoroughly unpacked it. The discussion clearly defines the boundaries of what the paper achieved and sets the stage for future research into that highly degenerate merger point. The primary task analyzing instabilities near the incoherent state via amplitude expansions is complete. ### processing final sections. Pages 42-46.
The final sections are brief. Section 5 has acknowledgments, notably mentioning helpful conversations with Steve Strogatz, another major figure in the field.
Yes, collaboration and discussion are key in science.
Section 6 provides the figure captions. We've implicitly discussed their content. Figure 1 shows the parameter space boundaries. Kalovas, take a list of Bogdanov point. Figure 2 illustrates the Hopf bifurcation scenarios governed by Hopf and $. Figure 3 compares frequencies. Figure 4 summarizes the resulting stable nonlinear states.
They visually summarize the key analytical results.
And Section 7 lists the references, which provide the historical context, Winfrey, Kuramoto, and the foundational mathematical tools like bifurcation theory text by Golubitsky et al., operator theory by Reed and Simon, used throughout the paper.
Essential for grounding the work and allowing others to delve deeper.
Okay, that seems to cover the final apparatus of the paper. We've reached the end of the document. # outro. So we started this deep dive, tackling a truly seminal work in mathematical physics, guided by this protocol of extreme granularity. Our goal was to understand not just the results, but the intricate logical and mathematical pathway, from the simple microscopic Kuramoto equation to the complex macroscopic behavior of synchronization. We saw the power of moving to the continuum limit with the Fokker-Planck equation.
And then the incredible simplification afforded by center manifold reduction, focusing the dynamics on just a few critical modes near the bifurcation points.
And the absolute centrality of O2 symmetry, derived from a simple assumption about the frequency distribution, which dictated the structure of the instabilities.
The key takeaways are really clear now, I think. First, that fundamental difference from Vlasov-type instabilities. The nonlinear coefficients governing synchronization stability in this Kuramoto-Fokker-Planck system remain finite and well-behaved even as the noise dollars vanishes. The theory doesn't break down.
Second, the mandatory eigenvalue degeneracy imposed by O2 symmetry, especially for the Hopf bifurcation. That multiplicity 2 complex eigenvalue was the crucial piece missed in some earlier work.
Which led directly to the third major takeaway, the rigorous proof, using the full O2 symmetric center manifold analysis, that for the bimodal population, the Hopf bifurcation generates stable standing waves alongside unstable traveling waves. This corrected the record and provided a solid theoretical foundation for understanding wave patterns in these systems.
It really underscores how the specific shape of the frequency distribution omega can determine whether synchronization leads to a steady state or complex, stable oscillations.
Absolutely. And this leaves us with a final thought for you, the listener. We've established that the complexity of synchronization dynamics escalates dramatically near that highly degenerate Takens-Bogdanov point, that knife-edge balance where steady order meets oscillatory instability. Now consider that coupled oscillators are ubiquitous. They model neurons firing in the brain, pacemaker cells in the heart, flashing fireflies, Josephson junctions, even power grids trying to stay synchronized. What observable real-world systems might actually be operating perilously close to such a codimension 2 point? Where just a tiny change in conditions could tip the entire system from smooth, stable collective behavior into explosive oscillations or complex, unpredictable dynamics. Where might this delicate mathematical crossroads be physically realized?
Welcome to the Deep Dive, where we extract the core knowledge from the most formidable source material. Today, we are undertaking a deep exploration into the very foundation of synchronized dynamics, the mathematics that explains how millions of decentralized units suddenly begin to move as one.
That's right. We are diving into a monumental work of mathematical physics, John David Crawford's 1993 paper, Amplitude Expansions for Instabilities and Populations of Globally Coupled Oscillators. This paper isn't just theory, it's a necessary corrective. Crawford uses highly rigorous tools, bifurcation theory and center manifold reduction, to settle a key debate and fundamentally reshape our understanding of synchronization onset in large populations.
Our mission is uncompromising. We are going through this document with extreme granularity, but we are doing it conversationally. We're breaking down the science, the math, and the underlying logic, ensuring that you, the listener, understand not just what was found, but why every mathematical step was necessary to achieve that finding.
To frame this deep dive, the paper addresses the moment synchronization begins, the transition from an initially disordered or incoherent state to collective order. This understanding is critical across, well, biology, engineering, and even physics.
The paper is foundational, authored by John David Crawford from the Department of Physics and Astronomy at the University of Pittsburgh. Let's start at the beginning, processing the abstract. #tag processing the abstract, linear progression and granularity. Okay, the first sentence. We analyzed the nonlinear dynamics near the incoherent state in a mean field model of coupled oscillators. This immediately establishes the domain of the problem. Why must the dynamics be nonlinear?
Well, they have to be nonlinear because synchronization itself is fundamentally a nonlinear outcome. If the system were linear, any initial disturbance would either just, grow infinitely or simply decay away.
Right, no stable collective behavior.
Exactly. Synchronization is about stable, self-sustaining collective behavior, the whole being more than the sum of its parts. And that absolutely requires nonlinear feedback mechanisms. And we're focusing on the behavior near the incoherent state, which is basically the starting point, the equilibrium, where all oscillators are just randomly scattered in phase, giving you zero net order.
And the mean field model, that sounds like the standard simplification for dealing with massive numbers of oscillators, right?
Precisely. When the number of oscillators, let's call it $9, is huge, we can't possibly track them all individually. So the mean field approximation lets us assume each oscillator interacts more or less equally with the average state of the entire population.
So you trade n individual equations for one statistical description.
That's the idea. It makes the problem tractable.
Okay, that sets the goal. First sentence covered. Have we missed any nuances there?
No, I think we've thoroughly unpacked it. That lays out the basic setup. Let's proceed to the next sentence.
All right, sentence 2 is much denser. It defines the whole mathematical approach. The population is described by a Fokker-Planck equation for the distribution of phases, and we apply center manifold reduction to obtain the amplitude equations for steady state and Hopf bifurcation from the equilibrium state with a uniform phase distribution. Phew!
Okay, yeah, we absolutely have to pause here. This sentence is the toolbox. First up, the Fokker-Planck equation.
Right. That rings a bell from statistical mechanics.
It does. It's a partial differential equation.
Yeah.
It governs how the probability density function here, the distribution of phases, usually denoted lower, evolves over time. We use it because we're assuming no dollars is effectively infinite, the continuum limit.
So it traps the crowd, not the individuals, and
Exactly.
it handles both the interactions and the randomness.
Exactly. It simultaneously accounts for the deterministic forces, which is the coupling between oscillators pulling them together, and the random forces, think of it as external noise, which causes diffusion, spreading things out in phase space.
Yeah.
It's got both drift and diffusion terms.
Okay, so that's the master equation for the population density. Now, the second tool, center manifold reduction. How does that help solve this presumably a very complex Fokker-Planck equation?
Right. Center manifold reduction is really a cornerstone of modern dynamical systems theory. When a system loses stability when it hits a bifurcation point, the instability doesn't usually happen everywhere at once. It tends to concentrate along just a few critical, slow directions or modes.
Okay.
The center manifold theorem provides the mathematical machinery to isolate precisely those critical directions. It lets us essentially collapse the infinite dimensional Fokker-Planck system down to just a handful of much simpler finite dimensional equations called amplitude equations.
Ah, so you zoom in on the important part of the dynamics right near the tipping point.
You got it. These amplitude equations capture the essential long-term behavior right near that instability, that bifurcation point.
And the sentence mentions two specific types of instabilities, or bifurcations.
Yes. The paper analyzes two key types that can arise from this uniform incoherent state. First, steady-state bifurcation. This is where the system transitions from the equilibrium state, the random incoherent one, to a new, stable, time-independent synchronized state. Think of it as the oscillators locking into a fixed pattern. The order parameter R becomes positive and constant.
Then the second.
The second is Hopf bifurcation. In this case, the system transitions from that same equilibrium to a stable time-periodic state. So instead of just locking, the collective state starts oscillating in a regular way. You might get waves or pulsing behavior.
And both of these emerge from the uniform phase distribution, which is just another way of saying that initial incoherent random state.
Precisely. That uniform distribution is the equilibrium that loses stability.
Okay, that covers the second sentence. That's the core mathematical framework. Fokker-Planck plus center manifold leading to amplitude equations for these two bifurcation types. Did we nail down the link between the uniform distribution and equilibrium sufficiently?
I think we've thoroughly unpacked it, yeah. The listener should understand that uniform phase distribution is the mathematical description of the incoherent state, the system at rest, before synchrony kicks in. Let's move on.
Sentence 3 introduces a really important condition. When the population is described by a native frequency distribution that is reflection symmetric about 0, the problem has circular symmetry. Symmetry is always powerful in physics and math.
Absolutely critical here. So reflection symmetric about 0 means the distribution of the oscillator's natural frequencies, let's call it g omega, g omega omega, is an even function. Mathematically, g omega equals g of minus omega.
Meaning for every oscillator wanting to spin, say, clockwise at a certain speed, there's a matching one wanting to spin counterclockwise at the same speed, a perfect balance.
That's exactly it. And this perfect balance confers a very specific type of symmetry onto the whole problem, O2 symmetry. This is also called circular symmetry. It includes both continuous rotations, shifting all phases, and discrete reflections, flipping the sign of phases and frequencies.
And why is that O2 symmetry so important?
Because it dramatically constrains the possible dynamics. It dictates things like the degeneracy of eigenvalues, how many independent ways the system can go unstable at the same time. And, as we'll see, this is precisely what leads to the correction of prior work. It's not just a mathematical curiosity. It has direct physical consequences.
Okay, symmetry established as key. Let's go to sentence 4. This one highlights a major finding by contrasting it with another field. In the limit of 0 extrinsic noise, although the critical eigenvalues are embedded in the continuous spectrum, the nonlinear coefficients in the amplitude equation remain finite, in contrast to the singular behavior found in similar instabilities described by the Vlasov-Poisson equation.
Right. This is where things get really, really interesting, methodologically speaking. The paper draws a sharp contrast with systems described by the Vlasov-Poisson equation. Think collisionless plasmas or even galaxies interacting via gravity.
Those systems often show something called Landau damping, right?
Exactly, a kind of collisionless damping. Now, if you try to do a similar bifurcation analysis on those Vlasov instabilities, specifically looking at what happens at the damping parameter, which is analogous to the noise or diffusion, here goes to 0.
What happens?
The key nonlinear coefficients in the amplitude equation, so ones that tell you if the new state is stable or not, they often blow up. They become singular. Sometimes they diverge really sharply, like d3 to the minus 3. The math basically breaks down.
So trying to analyze the perfectly noise-free Vlasov system using these standard techniques is problematic because the crucial numbers become infinite.
Pretty much. You need very specialized, often quite complex mathematical techniques to handle those singularities. But Crawford's core finding here is for this system, the Kuramoto model, described by Fokker-Planck.
The coefficients stay finite.
Yes. Even though this system also has the complexity of critical eigenvalues being embedded in a continuous spectrum, the nonlinear coefficients derived from the center manifold reduction remain finite as the noise dollar approaches 0 to 2-wetter.
Wow. Okay, that's a huge distinction. It means the synchronization transition here is mathematically, well, better behaved, more robust against the 0 noise limit.
That's a great way to put it. It's a fundamental difference in the mathematical stability properties of these two major classes of infinite dimensional systems. It validates, using amplitude expansions here, even in the idealized noise-free case.
A really significant point. Okay, sentence 5 introduces a specific scenario where the complexity peaks. For a bimodal reflection symmetric distribution, both types of bifurcation are possible, and they coincide at a codimension 2 Takens-Bogdanov point.
Right. So first, bimodal distribution. That just means the frequency distribution Goregolev omega has 2 peaks instead of 1. Imagine 2 distinct groups of oscillators, maybe centered around positive and negative frequencies.
So they're sort of pulling in different directions.
Exactly. And this richer structure allows the system to potentially exhibit both kinds of instability. We talked about the steady state one, where a real eigenvalue crosses zero, and the Hopf one, where a complex conjugate pair of eigenvalues crosses the imaginary axis.
And the sentences, they can coincide. They happen at the same time.
Yes, under specific conditions. When the parameters are tuned just right, the conditions for both the steady state and the Hopf bifurcation can be met simultaneously. This is called a codimension 2 bifurcation.
Why codimension 2?
Because you generally need to tune two independent system parameters, maybe the coupling strength dollars and the separation between the two peaks in omega dollars of omega to hit this special point precisely. It's like finding a specific point on a 2D map, not just crossing a line.
And that specific point has a name.
Yes, that highly special, degenerate point where the steady state and Hopf bifurcations merge is known as the Takens-Bogdanov point. It's a famous organizing center for complex dynamics. Understanding what happens near this point tells you a lot about how different kinds of synchronization behaviors connect to each other.
Fascinating. Okay, let's look at sentences 6 and 7, which describe the actual physical states that emerge and their stability. The steady state bifurcation may be supercritical or subcritical and produces a time-independent synchronized state. The Hopf bifurcation produces both supercritical stable standing waves and supercritical unstable traveling waves.
Okay, two new terms here, supercritical and subcritical. What do they mean?
Right, supercritical means the new state, the synchronized state, or the wave is stable, and it emerges sort of gently or continuously as you increase the control parameter, like the coupling dollars.
So you get a smooth transition.
Yeah. Subcritical, on the other hand, means the new state is actually unstable when it first appears, often below the critical point Casey-Fay. This can lead to abrupt jumps, hysteresis, where the system state depends on its history, or what people sometimes call hard transitions.
Got it. And the sentences describe the outcomes. Steady state gives you a time-independent, synchronized state, like we said, $3 and constant. What about the Hopf?
The Hopf bifurcation, according to the sentence, yields time-periodic states, specifically waves, and it claims there are two types generated: stable standing waves, SW.
What are those?
Imagine synchronized clumps of oscillators, maybe oscillating out of phase with each other, but the overall pattern remains fixed in space, or rather, fixed in phase. They stand still while oscillating internally.
Okay. And the other type?
And unstable traveling waves, TW. This would correspond to a single synchronized clump actively circulating around the phase circle, like a wave traveling around.
And crucially, the abstract states the SW are stable, but the TW are unstable. This leads directly into the correction of previous work, right? Sentences 8 and 9. It's exactly. Previous work on the Hopf bifurcation in a bimodal population by Bonilla, Nuyu, and Spigler, and Okuda and Kuramoto predicted stable traveling waves and stable standing waves, respectively. A comparison to these previous calculations shows that the prediction of stable traveling waves results from a failure to include all unstable modes.
This is really the core argument of the paper, isn't it? Crawford is saying, look, Bonilla and colleagues got the stability of the traveling wave wrong. Why?
Why? Because, as we discussed, the system with a symmetric Gebel-Gellers of omega has O2 symmetry. That symmetry forces the complex eigenvalue driving the Hopf bifurcation to be multiplicity 2. It's degenerate. There isn't just one way for it to go unstable. There are two linearly independent ways, related by reflection.
And Bonilla et al. Only considered one of them.
That's the claim. They effectively missed or neglected the second eigenvector, the one associated with the reflection symmetry. By doing so, their mathematical model, specifically their center manifold reduction, was incomplete. It didn't capture the full dynamics dictated by the symmetry.
And that incompleteness led them to calculate the traveling wave as stable, when in fact, if you include the full picture required by O2 symmetry,
You find the traveling wave is actually unstable, and the standing wave is the stable outcome. It's a beautiful example of how rigorously applying symmetry principles is essential for getting the physics right.
a major correction based on fundamental principles. The final sentence just lists keywords: oscillators, bifurcation, symmetry. Okay, mandatory verification. We've dissected the abstract sentence by sentence. We covered the model, the methods, the Vlasov contrast, the Takens-Bogdanov point, and the central correction regarding wave stability due to O2 symmetry. Have we missed any critical rhetorical purpose of the abstract?
I think we've thoroughly unpacked it. The abstract does exactly what it should. It summarizes the problem, the methods, the key results, and flags the main intellectual contribution, particularly that correction of prior work. It sets the stage perfectly for the details to come. Let's proceed to the paper's introduction.
All right, Section 1, Paragraph 1.1. It starts by setting the historical context, mentioning pioneers like Winfrey and Kuramoto, and then introduces the foundational microscopic model, the Kuramoto model, in Formula 1.
Yes, equation 1 is the starting point for almost all work in this area. It describes the phase dynamics of the ith oscillator. Let's read it out. Omega I plus k frac 1 and sto j plus k dot sub I equals omega sub I plus k over n times the sum from j equals 1 to n of sine of theta sub j minus theta sub I plus e chi sub I of t.
Let's break that down. Theta dot sub I is the rate of change of the phase of oscillator day.
Right. Omega sub I is its natural frequency, how fast it would spin on its own.
Then the big summation term is the interaction. Tauler is the coupling strength.
Scaled by NDI nullars for the mean field nature. And the interaction itself depends on the sign of the phase difference between oscillator j dollar and oscillator day, and sine of theta sub j minus theta sub I. This specific sign coupling is what makes the model mathematically tractable and physically rich.
And finally, Sakurai sub I of t is a noise term representing random fluctuations, which Sakaguchi added later.
Exactly. That basic equation, despite its simplicity, captures the essence of synchronization.
Okay, paragraph 1.2 introduces the way to measure synchronization. The complex order parameter, L of t times e to the IPI of t, defined in Formula 2.
Right. Formula 2 is dre IP1 times the sum from j equals 1 to n of e to the I theta sub j of t.
So you represent each oscillator's phase as a point on the unit circle in the complex plane e to the I theta sub j, and then you just find the center of mass of all those points.
Precisely. 3r is the magnitude of that center of mass vector. If the phases theta, L, I theta sub j are all scattered randomly, 3r's will be close to 0. If they all line up, 3r will be close to 1. So 2r measures the degree of coherence or synchronization.
And PSID is the phase of that center of mass, the average phase of the synchronized group.
Yep. The transition to synchronization is marked by $3 increasing significantly from 0.
Then Formula 3 gives Kuramoto's famous result for the critical coupling strength, KCC, needed for synchronization to start, at least in the noise-free case, for a simple frequency distribution.
That's DDC PZ0 K sub C equals 2 over pi times G of 0. Here, G dollars of 0 is the value of the frequency distribution right at the center frequency, usually assumed to be 0 after shifting.
So this tells you that if the oscillators are tightly clustered in frequency, meaning G dollars is large, you need less coupling, KC dollars is smaller, to get them to sync up. Makes intuitive sense.
It does. The threshold for synchrony depends directly on how diverse the oscillators are new the average frequency.
Okay, we've covered the first 3 paragraphs, the microscopic model, the order parameter, and the classic critical coupling. Have we captured the essence of this setup?
I think so. We have the individual oscillator dynamics and the way to measure the collective state. The next logical step, taken in paragraph 1.3, is moving from these non-dollar individual equations to a description of the whole population distribution, especially when dollar is very large. This requires the Fokker-Planck equation.
Right. Paragraph 1.4 introduces the Fokker-Planck equation itself, Formula 4, following Sakaguchi's work incorporating noise.
The equation 4 is Fokker partial d, the partial derivative of rho with respect to t, plus the partial derivative of rho times v with respect to theta, equals d times the second partial derivative of rho with respect to theta squared.
Let's unpack that PDE. Kita omega, TIOO of theta omega, is the density function we talked about. It tells you the probability of finding an oscillator with natural frequency omega at face of theta at time.
Right. The first term, partial Harshal t, partial rho partial t, is just the rate of change of density at a point.
The second term, partial theta, partial rho v partial theta, looks like a continuity equation term or a drift term. It describes how the density flows due to the phase velocity of dollar.
Exactly. It represents the deterministic movement of oscillators due to their natural frequencies and the coupling. It's conservation of oscillators.
And the term on the right, dilla dollar partial theta tiller deal times second partial rho partial theta squared, that's the diffusion term, due to noise.
That's the one. Del V is the diffusion coefficient related to the strength of the noise I sub I of t. It causes the distribution to spread out in phase, counteracting the synchronizing effect of the coupling.
So the equation balances drift from frequency and coupling and diffusion from noise. The paragraph also defines Darhove more formally. D omega times G omega times D of omega times drove of theta omega t to d the omega is the number of oscillators in a little phase frequency box.
And crucially, paragraph 1.4 includes the normalization condition, Formula 5.
It's an interrogant. The integral from 0 to 2 pi of d theta rho of theta omega t equals 1. This just says that for any given frequency omega omega, if you sum up the density over all possible phases theta theta from 0 to $2 pi, you have to get 1 or 100%. All the oscillators have to be somewhere.
It's a fundamental constraint.
Okay, paragraphs 1.4 done. Fokker-Planck defined. Let's proceed.
Paragraphs 1.5 and 1.6 now simply rewrite the phase velocity from EQ1 and the order parameter from EQ2 using this continuous tensity UT.
Formula 7 gives the velocity field valor felt by an oscillator, Pythagoras theta omega plus k omega plus k omega plus krat 6 thetas of theta omega t equals omega plus kr of t sine of t I minus the theta.
You see how it depends on the oscillator's own frequency omega, but also on the macroscopic state of the system through the order parameter theta nullus of t and the average phase pi psi of t. This is the essence of mean field coupling.
And Formula 8 gives the order parameter itself, now as an integral over the distribution. E zeta will theta omega omega ei theta r t times e to the iki of t equals the integral from 0 to 2 p omega d theta times the integral from minus infinity to infinity of d omega of rho of theta omega t times g omega times e to the I theta.
This is the continuum equivalent of the sum we had in Formula 2. You're averaging ei theta to the I theta over all oscillators, weighted by their density saw and frequency distribution to omega to omega.
At velocity and order parameter now in continuum form. Paragraph 1.7 then formally defines the noise I sub I of t that leads to the diffusion coefficient dollars.
Right. It assumes Gaussian white noise. The key statistical property is given in Formula 10. This is important.
Okay, Formula 10 is theta wrangle 2d delta L, the expectation value or average of A sub I of S times say val sub j of t equals 2d times delta sub I times delta of S minus t.
Let's break down those delta functions. Delta sub I is the Kronecker delta. It's 1 if 1 HAG or any trade jaw. This means the noise is uncorrelated between different oscillators. What happens to oscillator Ariel doesn't directly affect oscillator Giles noise.
Okay, independent noise sources.
Delta S of S minus T is the Dirac delta function. It's essentially infinite if T2 were idle otherwise. This means the noise is instantaneous in time. It has no memory. White noise.
And the coefficient 2 to dollars is the crucial link.
Yes. The strength of these microscopic uncorrelated fluctuations, quantified by $2, is precisely what determines the magnitude dollars the diffusion term in the macroscopic Fokker-Planck equation. This formula provides the rigorous connection between the micro and macro descriptions of noise.
Got it. Paragraphs 1.7 covered. Any nuances missed on the noise definition?
No, I think that's clear. The 2 to Dal factor is conventional and connects the noise variance rate to the diffusion constant. Let's move to the linearization.
Right. Paragraphs 1.8 and 1.9. This is standard practice for stability analysis. You look at small deviations from the equilibrium state. Here, the equilibrium is the uniform distribution 1 whole, not equals 1 over 2 pi, completely random phases.
And we define keta omega theta of theta omega t as the small deviation from this uniform state, 1 whole plus et. Then you plug this into the Fokker-Planck equation 4 and keep only the terms linear in keta.
Which leads to Formula 11, the linearized evolution equation for the deviation theta.
Partial eta plus n, the partial derivative of eta with respect to t equals L eta plus n of eta. Although strictly speaking, for linearization, we initially ignore $0 of eta represents the nonlinear terms that were dropped.
Okay, so the stability is governed by the linear operator $. Formula 12 gives the explicit form of $. It looks complicated.
Let's break down leta of eta. Formula 12 defines it as leta of eta, omega theta, Thursel theta e theta plus omega theta plus ccc d theta, defined as d times the second partial derivative of eta with respect to theta squared minus omega times the partial derivative of eta with respect to theta plus k head naught over 2 times the quantity e to the minus I theta times the integral of d theta prime and d omega prime of eta times g times e to the n theta prime plus complex conjugate.
Okay, let's dissect that. The first term, $, partial eta partial eta times second partial theta squared, that's clearly the diffusion acting on the deviation.
Right. The second term, omega partial theta minus omega partial theta, represents a rotation of the deviation due to the natural frequency omega.
And the third term, the one with the integral, that's the coupling.
That's the linearized effect of the mean field coupling. Notice it involves an integral of te eta, weighted by te omega of omega prime and eta n to the theta prime. That integral is essentially calculating the deviation in the order parameter caused by theta.
Ah, I see. So the evolution of theta at a point omega theta, omega depends on the integrated collective state deviation. That makes $, a non-local operator.
Precisely. That non-local integral term is the source of all the interesting collective behavior and much of the mathematical complexity. The CC just means complex conjugate of the preceding integral term, ensuring later is real if theta is real.
And Formula 13 just gives the form of the nonlinear terms non-nullars of eta, which were ignored in the linearization but are crucial for what happens after the instability starts. They involve products of theta and its derivatives.
Right, they provide the saturation mechanism that stops the initial exponential growth predicted by $.
Okay, mandatory verification check. We've introduced the full continuum equation for the deviation Keeler 8, split into its linear operator, nonlinear part, and nonlinear part. Have we grasped the why of this structure? Why separate line dollars?
Yes, I think we have. The structure partial eta plus n eta, partial t equals L eta plus n eta is absolutely standard for bifurcation analysis. The linear part dollar tells you when the equilibrium, the incoherent state, becomes unstable. Its eigenvalues determine the bifurcation point PLZ-tellers. The nonlinear part null tells you what happens next. Does the system settle into a new synchronized state? Does it oscillate? And is that new state stable? That's determined by non-dollar. We are now perfectly set up to discuss the crucial role of symmetry.
Excellent. Paragraph 1.810 gets right into it. The O2 symmetry, it arises, as we said, if the frequency distribution, the omega, is reflection symmetric. Formula 18. What are the generators of this symmetry?
The O2 group is generated by two basic operations acting on the data omega space. First, rotations, given by formula 15. Theta plus phi theta omega equals theta plus phi omega. This just means shifting all phases by a constant amount. Theta over d leaves the physics unchanged.
Makes sense. What's the second operation?
Reflections, given by formula 16. Theta omega, kappa dot theta omega equals minus theta minus omega.
So this reflection kappa kappa simultaneously reverses the phase angle and the natural frequency omega to omega.
Exactly. It corresponds to looking at the system in a mirror, effectively reversing the direction of rotation for everyone. The system's equations, specifically the Fokker-Planck equation with the structure of 9 and $, remain unchanged under both rotations. And reflections kappa, if and only if the frequency distribution d omega is even, meaning d omega dollar omega equals g of minus omega, which is formula 18.
So that even u omega grammars of omega is the necessary condition for the full O2 symmetry.
Correct. This symmetry will have profound consequences for the spectrum of dollars and the form of the amplitude equations.
Paragraphs 1.11 and 1.12 offer some refinements. Even if the mean frequency isn't zero, you can shift to a rotating frame, formula 19, to recover the symmetry, potentially. And if nu omega glarms of omega isn't reflection symmetric, you lose the reflection part, but you might still have rotational symmetry, which is SO2.
Right. O2 is the richer symmetry group containing both rotations, SO2, and reflections. The paper focuses on the O2 case because it's common and reveals the degeneracy issue missed by prior work.
Okay, paragraph 1.13 summarizes the linear stability results. Building on work by Strogatz and Marolo, it talks about the spectrum of the linear operator dollars.
Yes, they show that dollars has a continuous spectrum. These are eigenvalues that form a continuous set, typically corresponding to damped modes. For this system, they found this continuous spectrum lies along the vertical line, text re lambda dollar d, real part of lambda equals minus d in the complex plane.
Meaning modes associated with the continuous spectrum always decay, since d to noise is positive.
Generally, yes. This decay is related to phase mixing, analogous to Landau damping in plasmas. Oscillators with different frequencies naturally drift apart, destroying coherence. So for coupling dollars below the critical value phi d, the incoherent state d of dollars is stable. All perturbations decay.
But what happens when d exceeds d to dollars?
Then, a discrete eigenvalue lambda emerges from this continuous spectrum. If e to omega is unimodal and symmetric, this eigenvalue is real. It moves to the right across the imaginary axis into the right half plane. A positive real part means exponential growth.
So lambda dully signifies the instability, the onset of synchronization.
Precisely. And formula 21 gives a critical coupling d to the presence of noise dollars.
Let's read that. D to omega d2 plus omega 2 plus omega 2 1k sub c equals the inverse of the integral from minus infinity to infinity of d to g of omega d Bowman over d squared plus omega squared.
This is Sakaguchi's result. It generalizes Kuramoto's noise-free formula 3. You can see that as d to 2, the denominator becomes omega 2, and the integral involves d to omega to the goal if a gamut is sharply peaked. This integral might be tricky, but for well-behaved Daiga 2, you can show it recovers Kuramoto's result. The key point is that kineta depends on the entire shape of d dollar when noise is present.
Okay, linear stability understood. Continuous spectrum plus potential discrete eigenvalues crossing the imaginary axis at $2. Paragraphs 1.14 and 1.15 then bring us back to the specific controversy the paper aims to resolve.
Right. It mentions the work by Bonilla, New, and Spigler, BNS. They studied bimodal distributions and found a Hopf bifurcation leading to oscillations. But Crawford states their analysis failed to include both unstable eigenvectors that are required by the O2 degeneracy we just discussed.
We'll see the details later, but the claim is their math missed a crucial consequence of the symmetry.
Exactly. It also mentions Okuda and Kuramoto, who studied a related model of two interacting populations. Their model is actually a special case of the general Fokker-Planck equation here. They did find both traveling and standing wave solutions, and found the standing waves were stable, consistent with Crawford's later findings. However, the paper notes they didn't explicitly connect their results to the underlying O2 symmetry.
So BNS potentially made a mistake due to symmetry, while OK got results consistent with the symmetry, but maybe didn't frame it that way.
That seems to be the context Crawford is setting up. He's providing the unifying theoretical framework O2 bifurcation theory to explain and correct these earlier findings.
Okay, paragraph 1.16 then outlines the paper's structure. Section 2 will delve into the linear theory, clarifying the spectrum, eigenvalues, including non-semi-simple ones at the Takens-Bogdanov point. Section 3 will derive the amplitude equations using center manifold reduction.
Standard structure for a bifurcation analysis paper. Linear theory first, then nonlinear analysis.
And paragraph 1.17 hammers home the key messages again. It re-emphasizes the contrast with Vlasov systems. Coefficients here remain finite as Dirichlet-Ballers. It stresses the use of established O2 bifurcation theory.
And it previews the results for the bimodal case. The steady-state bifurcation can be super or subcritical. The Hopf bifurcation yields supercritical stable standing waves, SW, and supercritical unstable traveling waves, TW. This directly contradicts the BNS claim of stable TW.
Okay, mandatory verification for Section 1. We finished the introduction. It set up the Kuramoto-Fokker-Planck framework, introduced the crucial O2 symmetry, summarized the linear stability picture, TCR, highlighted the discrepancy in previous Hopf results, and outlined the paper's mission to resolve this using rigorous O2 theory, while also contrasting with Vlasov physics. Have we missed any critical details before diving into the spectrum analysis in Section 2?
I think we've thoroughly unpacked it. We understand the model, the key players, dollars, the importance of symmetry, and the specific scientific question being addressed regarding the stability of waves. We have the necessary context for the deep dive into the linear operator dollar and its spectrum. Let's proceed.
All right, Section 2. Linear theory. This is where the mathematical heavy lifting begins to analyze the operator dollar. Paragraph 2.1 starts by simplifying things using a Fourier expansion in the phase variable the theta.
Right. Since everything is $2 periodic in the theta, it's natural to expand the deviation, eta theta, of theta omega in a Fourier series. Formula 22 gives this expansion. Eta theta omega, eta theta omega equals the sum from L equals minus infinity to infinity of eta sub L of omega times e to the IL theta.
So you replace the function of two variables, a data emitter of theta omega, with an infinite set of functions, eta sub L of omega, each depending only on frequency omega. How does this help with the operator?
It effectively decouples the operator dollar with respect to the Fourier index dollars.
Yeah.
As shown in Formula 23, LE equals the sum from L equals minus infinity to infinity of L sub LE sub L times e to the IL theta. We now have a separate linear operator dollars acting on each Fourier mode, EDL.
And Formula 24 gives the explicit form of IL. This looks much simpler than the original calc.
It is. Let's read LE sub LALEL LELELD LA sub LALELD LA plus pyro K LALD LA sub L equals minus IL times the quantity omega minus ILD times LA sub L plus pyro naught K times the quantity delta sub L comma 1 plus delta sub L minus 1 times the integral from minus infinity to infinity of D omega prime omega prime eta sub L of omega prime.
Okay, let's break that down. The first term, IL omega LLD, IL minus IL times omega minus ILD times eta sub L, seems to contain the rotation and diffusion DLD.
Correct. Those are local terms acting only on edel sub L of omega at frequency omega.
The second term is the coupling. And look at those Kronecker deltas, delta sub L comma 1 and 8 gol A01, 8 delta sub L comma minus 1. They are 0 unless dollars is exactly 1 or NECA 1.
This is huge simplification. It means the non-local coupling term, the integral over to omega prime, only exists for the little 1 at 11 and one of the one Fourier modes.
So modes with 1, 0, and 2 only have the simple rotation and diffusion. They don't feel the collective coupling directly.
Exactly. Their dynamics are much simpler and, as we'll see, typically just damped. The interesting instability dynamics driving synchronization are entirely contained within the little 1 and 11 modes.
That explains why the order parameter ESI involves only the first Fourier component, E eta theta. Also, formula 25 reminds us that eta sub L equals 0 is identically 0.
Right. That follows from the normalization condition. Integral of A to Rho must be 0, which means the Leller over Fourier component must vanish.
Okay, paragraph 2.1 done. Fourier expansion simplifies dollar dramatically, isolating the coupling to PRA1. What's next?
Paragraph 2.2 introduces the necessary mathematical tools for dealing with eigenvalues and projections in this function space setting. The inner product, formula 26, and the adjoint operator, Ledager, formulas 27, 28.
We need the adjoint operator, later dollar dagger, because we're in an infinite dimensional space, right? For projections.
Precisely. In finite dimensions, finding the component of a vector along an eigenvector is simple. In infinite dimensions, like our space of functions under omega right, if the operator Ledager isn't self-adjoint, and dollar here is not, the eigenvectors don't form a nice orthogonal basis.
So you need the eigenvectors of the adjoint operator, literal dollar?
Yes, the eigenvectors CRL of dollar and the eigenvectors eigendensidager of Ledager form a biorthogonal set. To project an arbitrary state 8 eta onto a specific eigenvector little dollar, you use the inner product with the corresponding adjoint eigenvector. This machinery is essential for the center manifold reduction later.
Okay, mandatory verification. We've set up the Fourier decomposition, found the structure of dollars, and introduced the adjoint Ledager needed for projections. Have we missed the strategic goal of the adjoint operator here?
No, I think we've nailed it. The adjoint Ledager and the inner product are the tools required to properly isolate the dynamics on the critical eigenspace when we perform the center manifold reduction. It's foundational for deriving the amplitude equations correctly. Let's proceed to the eigenvalue problem itself.
Paragraphs 2.3 and 2.4 set up the eigenvalue problem. Lambda pi equals lambda psi, formula 30. Using the Fourier decomposition, this becomes lambda L for each lambda labeled dollars.
Right. The paper then makes a crucial point. Based on the structure of lambda dollar 24, non-singular eigenfunctions, meaning well-behaved solutions, can exist only if lambda dollars.
Why is that?
For $1, the operator is just a ln all omega L2D. It's a simple multiplication operator in omega. Its spectrum is purely continuous, corresponding to lambda L omega LTD. These eigenvalues all have real Dabney dollars, which is negative, since T to D. So all modes with tilling to 2 are inherently damped and stable, regardless of the coupling dollars or the distribution data.
So the only possibility for an instability for an eigenvalue lambda to potentially cross into the right half plane, lambda dollar, comes from the Wellano or Alana 1 modes.
Exactly. The entire bifurcation analysis boils down to analyzing the spectrum of 1 along and a 1.
Okay. Paragraph 2.5 focuses on Wolin dollar. It introduces a scaling lambda equals minus ILZ for convenience, leading to equation 33. And it arrives at the condition for eigenvalues.
Yes. After some algebra, the eigenvalue equation for 1 along requires that the complex number ZL must be a root of a special function, the spectral function lambda sub LZ, provided we're looking for eigenvalues outside the continuous spectrum, i.e. text MZD-LD.
And formula 37 defines this crucial spectral function.
Lambda z to omega il, z equif 1 plus il freichu, defined as 1 plus ilk over 2 times the integral from minus infinity to infinity of d omega prime g of omega prime over omega prime minus z minus ILD.
So finding the discrete eigenvalues lambda of our original operator, the d dollars that can cause instability, is equivalent to finding the roots z dollars of this complex equation lambda 0, lambda sub L of z 0 equals 0.
Precisely. The roots z dollar of the spectral function lambda determine the point spectrum, the isolated eigenvalues that can actually emerge from the continuous spectrum background and drive the synchronization instability. This equation is central to the whole analysis.
Paragraph 2.6 then examines the symmetries of this spectral function lambda sub L of z, which connect back to the O2 symmetry of the problem.
Right. Two key identities are presented. First, formula 38. Lambda LZ. Lambda sub L of Z star equals lambda sub minus L of Z star. This relates the function for Weyl dollar to the function for L as a star. It ensures that if lambda is an eigenvalue, its complex conjugate lambda is also an eigenvalue corresponding to the opposite Fourier mode. Eigenvalues come in conjugate pairs.
Standard for real systems. What's the second identity?
The second one, formula 39, only holds if we have the full O2 symmetry, i.e. omega is even. Lambda L's at lambda all mana z, lambda sub L of Z star equals lambda sub L of main Z star.
How does this constrain the roots Z dollar?
If ZZ's is a root, so lambda L in this identity implies lambda ZL of Z as well. So a Z must also be a root. If CL is purely imaginary, meaning lambda is real, the steady state case, this doesn't add much. But if Z dollars has a non-zero real part, meaning lambda is complex, the Hopf case.
Then ZL and ZLove are distinct roots.
They are. This O2 symmetry guarantees that complex eigenvalues lambda, where R's late, must come not just in conjugate pairs lambda-lambda, but in sets of 4 related eigenvalues unless lambda is purely real or purely imaginary. This is the mathematical root of the eigenvalue degeneracy that Crawford argues B&S missed.
Okay, mandatory verification on the spectral function. We've defined lambda sub L of Z, shown its roots give the crucial eigenvalues, and seen how O2 symmetry imposes constraints, formula 39, leading to potential degeneracy for complex eigenvalues. Have we fully captured the geometric interpretation of these symmetry relations?
I believe so. We've established that relation 39 is the O2 guarantee of that extra symmetry in the root structure, which is absolutely critical for understanding the Hopf bifurcation correctly. It forces the degeneracy. Let's move on.
Paragraph 2.7 introduces more mathematical machinery. The projection operator lambda p sub lambda onto the generalized eigenspace E lambda E sub lambda, defined via a contour integral, formula 40, involving the resolvent operator lambda L or sub L of lambda equals lambda minus L sub L inverse, formulas 41 and 42.
This is standard functional analysis machinery for defining projections when you don't have a nice orthogonal basis. The key result is formula 43, which simplifies its projection considerably.
Lambda A1 plus fractionally R1 key sub lambda A equals e to the I theta over 2 pi I times integral over gamma naught d lambda prime R1 of lambda prime A1 plus e to the minus I theta over 2 pi I times integral over gamma naught d lambda prime R minus 1 of lambda prime A minus 1.
What this shows is that because the interesting eigenvalues lambda only arise from the little one and little sectors, the projection onto the critical eigenspace lambda only involves the little and Fourier components, eta 1 and L1 of the state dollar you're projecting. The higher harmonics don't contribute directly to the critical part.
Makes sense. Now we get into the specific types of eigenvalues, starting with subsection 2.1, simple roots and semi-simple eigenvalues.
Right. A simple root Z dollar of the spectral function is defined by formula 44. Lambda 1 is Z and L1. Lambda 1 of Z0 equals 0, but lambda 1 prime of Z0 is not 0. The derivative is non-zero. This leads to semi-simple eigenvalues, meaning there are enough eigenvectors to span the eigenspace. No generalized eigenvectors are needed yet.
Let's look at 2.1.1, real eigenvalues. This corresponds to Z dollars being purely imaginary, so lambda was used as real. This is the setup for the steady state bifurcation.
Correct. The key finding here is that even though the root C dollars is simple, the O2 symmetry ensures that the corresponding real eigenvalue lambda has 2 linearly independent eigenvectors. There's the primary eigenvector Sandeau, given by formula 46, and there's its reflection kappa Sandeau formula 48, which turns out to be just the complex conjugate psi star in this case.
So a simple root plus O2 symmetry implies a two-dimensional eigenspace for a real eigenvalue lambda.
Exactly. The paper then explicitly constructs the corresponding adjoint eigenvector C tilde and kappa san sign Sandeau, formulas 49 and 52, and confirms they satisfy the necessary biorthogonality relations, 53, 54.
And the projection onto this 2D center manifold is given by formula 56.
Yeah.
Lambda sanda plus kappa tai sub lambda eta equals inner product C tilde times C plus inner product kappa dot sign to tilde times kappa dot sign.
This explicitly shows that the dynamics near the steady state bifurcation under O2 symmetry are governed by 2 amplitudes, and Euris's to kappa dollars is 2-dimensional.
Okay, that's the real eigenvalue case. Now for 2.1.2. Complex eigenvalues. Here, zeta is complex, so lambda eigeners is complex. This leads to the Hopf bifurcation.
Again, O2 symmetry plays the critical role. If lambda is a complex eigenvalue arising from a simple root Z dollar, the symmetry guarantees that it must have multiplicity too. There are 2 linearly independent eigenvectors associated with the same complex eigenvalue lambda. These are Judith C dollars and its reflection kappa, say kappa dot eta, given in formula 57.
And their complex conjugates conjugate to chi are eigenvectors for the conjugate eigenvalue lambda.
Correct. So the full center manifold near the Hopf bifurcation point is four-dimensional, spanned by these four vectors. See kappa dot psi, kappa dot psi, kappa dot psi, psi star, kappa dot psi.
And this is the crucial point of contention. The multiplicity to degeneracy for the complex eigenvalue lambda spanned by side and kappa psi.
This is it. Crawford's argument is that the analysis by Bonilla et al. Effectively only considered the dynamics associated with size, neglecting the equally important modes kappa Sison's conjugate, which are mandated by the O2 symmetry.
The projection operator plam de eta in Formula 60 again confirms this structure, involving terms for both plays and kappa psi.
Yes, it projects onto that 2D eigenspace associated with lambda I and play ada projects onto the conjugate space.
Okay, mandatory verification for semi-simple eigenvalues. We've clarified that O2 symmetry mandates multiplicity to semi-simple eigenvalues lambda for both the real steady-state 2D center manifold for lambda dollars and complex Hopf 4D center manifold for lambda bifurcations. We've traced the connection from the simple root of lambda plus O symmetry to this eigenvector multiplicity. Is that connection solid?
Yes, I think we have established that clearly. A simple root of the spectral function, when combined with the constraints of O2 symmetry, forces the eigenvalues relevant to bifurcation, real lambda dollar and tanda, or complex lambda omega dollar to have a geometric multiplicity of 2.
Now let's briefly touch on the non-semi-simple case.
Subsection 2.2 deals with multiple roots and non-semi-simple eigenvalues. This happens when the root Zoligus is not simple, meaning lambda 1 Zoliers equals 0. Lambda 1 prime of 0 equals 0, as well as lambda 1 0 equals 0.
Right. When this happens, the eigenvalue lambda extendral IZU is non-semi-simple. This means you don't have enough regular eigenvectors to span the relevant space. You need to introduce generalized eigenvectors, often denoted upsilon eigenvect.
What is a generalized eigenvector?
It's a vector that's not quite an eigenvector itself, but lambda acting on it gives you a true eigenvector, or another generalized eigenvector. See formula 62 is 73. They form chains, lambda epsilon plus solenoid. The subsection shows that such a generalized eigenvector upsilon exists for this system only if the root z dollars is non-simple, specifically if lambda 1 z equals 80 lazy Elios formula 67 and 68.
Yes, and the paper focuses on the case where this happens for a real eigenvalue lambda a, so C's is imaginary, lambda 1. This specific situation defines the Takens-Bogdanov point.
So the Takens-Bogdanov point is characterized by a non-semi-simple real eigenvalue lambda dollars.
Correct. At this point, the linear operator has a Jordan block structure. The paper then explicitly constructs the true eigenvector, and the generalized eigenvector upsilon, formula 71, for this case.
And again, due to O2 symmetry, we also have the reflected counterparts, capital and capital upsilon. Right.
And the corresponding adjoint system gives CGS tilde, and a generalized adjoint upsilon tilde at 7273, satisfying specific biorthogonality relations, 7477.
The final projection plam de eta for this non-semi-simple case, formula 84, shows that the center manifold at the Takens-Bogdanov point is four-dimensional, spanned by two eigenvectors,
Right.
phantom I, and two generalized eigenvectors, upsilon, kappa upsilon.
Yes.
Now this raises an important question again. Why go into all this technical detail about generalized eigenvectors and the Takens-Bogdanov point if the main focus is on the simpler steady state and Hopf bifurcations away from this point?
It's crucial because the Takens-Bogdanov point is the organizing center where the lines of steady state and Hopf bifurcations meet in the parameter space. To understand how these two simpler bifurcations connect, how one might turn into the other as you change parameters, you absolutely must understand the degenerate structure right at their meeting point. The behavior nearby is dictated by unfolding this non-semi-simple structure. That 4D space spanned by a pi, upsilon, kappa dot keti upsilon, is the minimal linear space needed to capture the dynamics right at that critical juncture.
I see. It's the linchpin connecting the two main phenomena.
Precisely.
Okay, subsection 2.3 then applies all this linear theory to a concrete example. The bimodal population described by two Lorentzian peaks, formula 85. G Miguel has peaks at G mega plus or minus omega naught with epsilon.
This specific choice allows for analytical calculations. Solving lambda 1 z obey d yields two roots, z o a z plus minus, formula 88. The nature of these roots, real or complex, depends on the parameters, t omega dollar and phi lambda dollar.
The analysis identifies the key parameter boundaries in figure 1.
Yes. Ka, where eigenvalues disappear into the continuum. Ka, Formula 90, where a real eigenvalue crosses zero. That's the steady-state bifurcation line. K by K Formula 91, where complex eigenvalues cross the imaginary axis. That's the Hopf bifurcation line.
And crucially, K-Bonilla is where the roots K collide, leading to the non-semi-simple eigenvalue, the Takens-Bogdanov line.
Right, and the paper notes that the Kd and Thaler lines meet at a specific point, the codimension 2 Takens-Bogdanov point, when K1 epsilon plus d and $, epsilon plus d.
So this example clearly shows how, by tuning parameters, like increasing the peak separation $, or you can transition from a steady-state instability to a Hopf instability with the Takens-Bogdanov point marking the transition.
Exactly, and it sets the stage for analyzing the nonlinear states, particularly the stable standing waves hypothesized by Kuramoto, which emerge from the Hopf bifurcation.
Okay, mandatory verification for Section 2. We've completed the entire linear theory section. We established the Fourier framework, the spectral function lambda, the critical role of O2 symmetry in forcing eigenvalue degeneracies, multiplicity 2 for semi-simple cases, the structure of the non-semi-simple Takens-Bogdanov point, and we saw how this plays out in the bimodal Lorentzian example, mapping the boundaries between different instability types. Have we missed any crucial details regarding the structure of the spectrum of Naldahl?
I think we've thoroughly unpacked it. We've seen the spectrum consists of the discrete eigenvalues, roots of lambda responsible for instability. Sitting on top of the continuous spectrum, the background C of damped modes at re lambda equals nil2d. That gives us the complete linear picture needed before we tackle the nonlinear dynamics in Section 3, which will tell us what actually happens as a result of these instabilities.
All right, Section 3 gets into the nonlinear analysis using center manifold reduction. Paragraph 3.1 starts by looking at the Fourier expansion of the nonlinear term dollars of eta.
Yes, Nada contains terms that are quadratic and higher order in the deviation data. Formula 95 shows its Fourier expansion. The key thing to notice is how it couples different Fourier modes.
It looks like terms involving the last Bay1 components of eta, which relate to the order parameter, multiply other components eta, generating higher harmonics like Tena, Thaler, 3-3 forms, etc.
Exactly. The nonlinear dynamics essentially take the energy growing in the unstable Keen-Tel1 modes and transfer it into the stable, damped, higher harmonic modes, where you have U2, PM3, that's Mon 3. This transfer is what eventually saturates the instability and leads to a stable, synchronized state or wave pattern. Hashtag 3.1, steady state bifurcation.
First, subsection 3.1 analyzes the steady state bifurcation. Here, we have a real simple eigenvalue lambda crossing 0 at KC-ABC. We know from section 2 that the center manifold is two-dimensional, spanned by CC and kappa psi C psi, and kappa dot psi equals psi star.
Right. The method involves splitting the full state tail into the part living on this 2D center manifold, delta bundle I plus alpha psi p sublum of eta equals alpha psi plus alpha psi psi star, using alpha as the complex amplitude, and the part living in the stable subspace, Hopf lambda.
Equations 96-102 set up this decomposition. The dynamics then split into an ODE for the amplitude alpha, EQ $99, and a PDE for the stable modes, EQ $100.
The core idea of center manifold reduction, subsection 3.1.1, is that near the bifurcation, the stable modes dollars are completely determined by, or slave to, the slow dynamics of the critical amplitudes alpha and alpha. We can write Serre dollars as function alpha s equals h of alpha, alpha star, EQ 103. So you can eliminate Serre-Zoll and get a closed equation for alpha alone.
Essentially, yes. And the O2 symmetry greatly simplifies this. It dictates that the evolution equation for alpha must take the form p sigma. Alpha alpha dot equals p of sigma times alpha, EQ 108, where sigma alpha 2 sigma equals mod alpha squared is the only invariant under rotations.
Which leads to the amplitude equation 109 alpha alpha lambda plus p sigma, alpha 2 plus alpha dot equals alpha times, lambda plus p sub sigma of 0 times mod alpha squared plus higher order terms.
This is the equation we were aiming for. Lambda is the linear growth rate, proportional to k sega. The crucial term is the real coefficient sigma, 0 par p sub sigma of 0, the first nonlinear coefficient. Its sign determines the stability and direction of the bifurcation. If sigma, the cubic term, is stabilizing, leading to a stable synchronized state with amplitude alpha to approx, lambda sigma, this is a supercritical case.
Right, if sigma 0 Sindo, the cubic term is destabilizing, leading to an unstable state near alpha severance. This is the subcritical case, often implying larger amplitude solutions or hysteresis.
The derivation also relies on the O2 constraints on the function ILO 116, 100, 416, 120, ensuring alpha dollar involves powers like alpha.
Correct. Subsection 3.1.2 then gets into the calculation of sigma. It turns out this coefficient arises from the interaction between the quadratic nonlinearity in althea and the linear operator dollar.
How does that work?
The quadratic terms in alter, when expressed in terms of alpha, generate terms like alpha 2 ei2 to the alpha squared e to the i2 theta. These act as a forcing term for the alta2 mode in the equation for the stable modes, Zevel-Nel.
Ah, so the land-ladder dynamics generate forcing at OFL2.
Exactly. This forces the LD2 component of 12 TP-tolers to have a response proportional to alpha 2y. We need to calculate the coefficient tangent2 sub 2 superscript 2 of omega of this response.
Formula 131 gives the solution for 22 dol. Ragby sub 2 superscript 2 of omega equals minus IPSI of omega over minus E0 minus I2D. It depends on the eigenvector I2Z and the system parameters.
Plugging this back into the projection formulas leads to the final expression for the cubic coefficient sigma over in formula 132. Lambda omega CP C pi I2 2 omega 0 ID2 omega 70 omega Z I2 2 sub sigma 0 equals minus pi squared K cubed over 2 lambda prime 1 of Z0 times the integral d omega G of omega over omega minus Z0 minus ID squared times omega minus Z0 minus I2D.
That looks like a complicated integral, but the paper emphasizes it must evaluate to a real number because of the O2 symmetry.
Yes, that serves as a consistency check.
Okay, now for the payoff in subsection 3.1.3. Applying this formula to the bimodal Lorentzian example, 85, along the steady-state bifurcation curve, x6 scale.
The calculation details omitted leads to formula 133, an explicit expression for sigma in terms of the parameters epsilon d omega dollar. The sign turns out to depend on the comparison between omega dual omega naught squared and a critical value omega to omega d squared, which depends on d ln epsilon.
And the conclusion is?
If the omega teaks are relatively close, then the sigma down super dollars. This means the bifurcation is supercritical, leading to a stable, partially synchronized state.
But if omega dollars peaks are far apart,
then zeta dollars of bifurcation is subcritical, meaning the small amplitude synchronized state is unstable. This suggests the system might jump to a large amplitude state or exhibit hysteresis. The shape of d dollar dictates the nature of the transition.
Fascinating. Subsection 3.1.4 revisits the d to dollar limit for this coefficient to sigma.
Right, the Vlasov contrast again. As d to dollar, the denominators in the integral for sigma, like omega 0 IDD, develop poles near the real axis, the omega approx 0 and the dollar approx 0 here.
Which looks dangerous, like it might diverge.
It does look dangerous. However, Crawford uses techniques from complex analysis, Plemmel formulas, analytic continuation, to carefully evaluate the integral in this limit. The conclusion is that, unlike in Vlasov-Poisson systems where similar coefficients often diverge, like d3 here sigma remains finite as d to the dollar.
Formula 139 gives the approximate result for small dollars. Into before p omega 2 d 2 Ginebrew partial omega 1 plus odp sub sigma 0 is approximately minus pg of 0 squared times second partial derivative of g of 0 wrt omega squared divided by integral from 0 to infinity d omega partial g partial omega over omega plus order d.
For typical unimodal symmetric profiles, where Vero's dollars, this suggests sigma dollar, meaning the bifurcation is generally supercritical in the low noise limit, consistent with Kuramoto's original findings.
So the steady-state bifurcation is well-behaved even without noise. Finally, 3.1.5 briefly considers what happens if you break the O2 symmetry by making omega slightly asymmetric.
If you break the reflection symmetry, the symmetry lambda is lost. This typically causes the real eigenvalue lambda dollar to split into a complex conjugate pair near the imaginary axis, turning the steady-state bifurcation into a Hopf bifurcation, generally leading to traveling wave solutions. The perfect O2 symmetry is needed for the pure steady-state bifurcation.
Okay, mandatory verification for the steady-state part. We've analyzed the steady-state bifurcation using center manifold reduction, derived the amplitude equation, and the crucial cubic coefficient sigma, seen how its sign determines super subcriticality in the bimodal example, and confirmed the coefficient remains finite as dollar to dollars, contrasting with Vlasov. Have we missed any connections or nuances?
I think we've thoroughly unpacked it. We understand how the synchronized state emerges or fails to emerge stably, and how its stability depends on the frequency distribution details. The next logical step, and the core of the paper's correction, is applying the same center manifold logic to the Hopf bifurcation. Hashtag 3.2 Hopf bifurcation, pages 29 to 41.
Right. Subsection 3.2 tackles the Hopf bifurcation. This occurs when a simple, complex eigenvalue pair lambda crosses the imaginary axis at k-ish. We established in section 2 that due to O2 symmetry, the center manifold is four-dimensional.
That's right. It's spanned by the eigenvectors C doc, kappa doc for eigenvalue lambda, and their conjugates bar for eigenvalue lambda. We need two complex amplitudes to describe the state on this manifold. Let's call them alpha and kea.
where alpha is associated with beta and beta is associated with the reflected mode, cap, eta, like...
Exactly. Beta 2 represents the amplitude of the mode that Crawford argues was neglected in the BNS analysis. The full state is decomposed as terta, alpha psi plus beta, kappa kappa plus beta psi 140, 148.
Subsection 3.2.1 focuses on the dynamics on the center manifold. Again, the stable modes are assumed slave to the amplitudes, H's, alpha, alpha, beta, beta, EQ, $149. This leads to coupled ODDs for alpha and beta, ELANS 50, 150, 151.
Now, we need to invoke the O2 symmetry constraints on these amplitude equations. How do alpha moda transform under rotation and reflection?
The paper states, rotation by beta acts as alpha beta, ei phi beta. Alpha beta equals e to the minus I phi alpha, e to the I phi beta. They pick up opposite phases.
And reflection kappa acts as kappa, beta alpha, kappa dot alpha beta equals beta alpha. It simply swaps the two amplitudes.
These symmetries, plus an additional phase shift symmetry inherent in the problem, severely restrict the form of the amplitude equations. They can be reduced to a standard O2 equivariant normal form for Hopf bifurcation given in formula 165.
Right. This normal form depends only on specific combinations of the amplitudes that are invariant under O2. These are $1, alpha 2 plus beta 2 equals mod alpha squared plus mod beta squared, total intensity, and delta equals mod beta squared minus mod alpha squared, intensity difference.
The dynamics eventually boil down to two coupled equations for the real amplitudes. Sex by dollar and 6 by dollar equals beta, given in formulas 168 to 169. These equations involve the linear growth rate in your thalers and two crucial cubic coefficients, which the paper calls pi molar and
Coefficients, Bannon and thalers, determine everything about the solutions and their stability near the Hopf bifurcation.
The analysis of these equations reveals two main types of solutions, summarized in Table 1.
Yes. First, traveling waves, TW. These correspond to solutions where only one mode is active, either XTW, virido meaning alpha next 0, beta, O 0, meaning alpha double, beta XTW store.
Physically, this represents that single circulating clump we talked about.
Exactly. The second solution type is standing waves, SW. These correspond to solutions where both modes are equally excited, 6W, XW, OVO, age, XSW, meaning alpha, beta, neck.
And physically, this is the state with two counter-propagating clumps, oscillating perhaps, but the overall pattern is stationary.
Correct. The frequency of oscillation omega capital omega near the bifurcation point is also determined by the analysis, formula 170.
So the linear theory's prediction of two modes, and kappa, naturally leads to two distinct nonlinear wave patterns, TW and SW. The big question is, which one is stable?
That depends entirely on the signs and relative magnitudes of those cubic coefficients.
Okay.
$3 and 3. Subsection 3.2.2 gets into their calculation.
It involves transforming coordinates to eliminate certain cubic terms and isolating the ones relevant to the normal form, EQ 175. The coefficients parse and are then expressed in terms of the underlying quadratic coefficients 2h sub 2 superscript I of the center manifold function. Total is 177, 178.
Similar to the steady-state case, these two $2 coefficients arise from the quadratic nonlinearities acting on the linear modes. You need to calculate the response of the lil $ and 2UT2 modes to the forcing generated by the KUA2A1 critical modes, EQ 179.
The paper explicitly calculates the required coefficients to H21, H22, H21, H20 in formulas 183, 185.
And importantly, it again confirms that these coefficients, and thus KUA2 remain finite as the noise dollars to dollars. The Vlasov contrast holds for the Hopf case too. Stable oscillations are possible even in the noise-free limit.
Okay, now for the results. Subsection 3.2.3 applies this to the bimodal Lorentzian example at the Hopf threshold 2 edge.
By analyzing the structure of the integrands involved in Pru, the paper concludes that for this example, Pru is always negative.
What does that imply?
It implies that the Hopf bifurcation itself is supercritical. Both the TW and SW solutions emerge smoothly as 2 increases past $2.
Okay, so no jumps or hysteresis expected here. What about stability? That depends on through dollars.
Right. The calculation shows that true dollar involves a term P epsilon D omega 2 P epsilon D omega naught squared, formula 192, which is demonstrated to be positive. This makes free art itself always positive for this model.
So a $2, $, and $3. What does this combination predict for the stability of SW and TW?
Let's look at the stability conditions derived from the normal form. For standing waves, SW's stability requires $2 plus $2, or effectively just Pru's not too negative. Since $2, both conditions are met. In fact, the stability eigenvalues are proportional to $2 and $4, both negative.
Conclusion. Standing waves are supercritical and stable.
Yes. Now, for traveling waves, TW. Stability requires plus R0 and $. Since poo-R0, the second condition poo-R0 is met. But the first condition, poo-tall is R0, 0, might fail if $2 is large and positive compared to $2.
Let's recheck the stability eigenvalues for TW. One is related to poo at R0, which is negative. What's the other?
The other eigenvalue governing perturbations that try to turn a TW into an SW is proportional to $2 plus R0. Oh, wait, let me check the standard O2. Hopf stability conditions again. For TW stability, we need $2 plus R0. Since $2 is negative, this condition is not guaranteed. In fact, the stability analysis, often expressed differently, shows TW are stable if RIers and unstable if
Traveling waves are supercritical but unstable.
There it is. The stable state emerging from the Hopf bifurcation is the standing wave, not the traveling wave.
Exactly. This directly contradicts the prediction of stable TW by Bonilla, New, and Spigler. Subsection 3.2.4 explicitly makes this comparison. It confirms that BNS effectively analyzed a system, EQ194, that only included the alpha mode equivalent to setting beta $sols. By neglecting the beta mode required by O2 symmetry, they missed the Daylil term entirely in their stability calculation.
Their analysis was mathematically correct for the reduced system they considered, but that system didn't fully represent the physics constrained by O2 symmetry. They missed the instability driven by the coupling between the alpha and beta modes, which is captured by $3.
And subsection 3.2.5 confirms that the earlier Okuda and Kuramoto model, which used two distinct populations, is a special case of this general Fokker-Planck setup, when epsilon couplings match EQs to 1 2 or 1 2 or 2. Their finding of stable SW is consistent with Crawford's O2 analysis.
Right. Oki got the right physical result for their specific model, and Crawford provides the general theoretical framework that explains why.
Finally, 3.2.6 considers breaking the O2 symmetry again.
If you perturb omega or break reflection symmetry, the multiplicity 2 complex eigenvalue lambda typically splits into two distinct complex conjugate pairs. This leads to two separate Hopf bifurcations, and the simple SW and TW solutions can perturb into more complex modulated waves.
Okay, mandatory verification for section 3. We meticulously derived the amplitude equations for both steady state and Hopf's bifurcations under O2 symmetry. We applied them to the bimodal example, finding potentially subcritical steady states but supercritical Hopf. Crucially, we established the stability hierarchy for the Hopf: stable standing waves and unstable traveling waves, thereby correcting the BNS result by including the full consequences of O2 degeneracy. Have we secured this main finding and its justification?
I think we've thoroughly unpacked it. The resolution of the stability controversy demonstrating stable SW and unstable TW emerged from the Hopf due to the O2 symmetry. Forcing the eigenvalue degeneracy and specific signs of free is the central achievement of the nonlinear analysis. The comparison with BNS clarifies exactly where their analysis fell short by not accounting for the full symmetry.
Section 4 provides a discussion and summary. Figure 4 nicely maps out the regions in parameter space where the different stable states exist, the incoherent state, the partially synchronized state from supercritical steady state, and the standing waves from supercritical Hopf.
Right, it visually summarizes the main outcomes. But the discussion immediately points to the boundaries between these stable states, particularly the dashed line in Figure 4 separating the synchronized state and the standing waves. Analyzing the transition there is non-trivial.
And it highlights the biggest remaining challenge: analyzing the dynamics near the O2-Takens-Bogdanov point, where the steady state and Hopf lines merge.
Exactly. The paper notes this is particularly complicated because in the bimodal example analyzed, the steady state bifurcation becomes subcritical near this merger point. Standard Takens-Bogdanov theory often assumes a supercritical steady state branch.
So the specific nature of the instability here requires going beyond the standard textbook analysis of the Takens-Bogdanov point.
It seems so. Crawford mentions that fully understanding this point might require dealing with higher-order nonlinear degeneracies, potentially involving fifth-order terms, or even necessitating analysis of a codimension 3 bifurcation, where three distinct instability conditions meet. It points towards significantly more complex dynamics right at that confluence.
A clear marker for challenging future research. Okay, mandatory verification for the discussion. We've covered the summary of stable states and the explicit identification of the O2 Takens-Bogdanov point, especially in the presence of subcriticality, as the major area needing further, more advanced analysis. Have we missed any nuances in the paper's concluding remarks or limitations?
I think we've captured it. The discussion accurately frames the achievements, analyzing the codimension 1 instabilities near the incoherent state while honestly acknowledging the significant complexities that remain at the codimension too, and potentially higher degeneracies. The primary task laid out in the abstract is complete. ### processing final sections, pages 42-46.
Okay, the final parts. Section 5 has acknowledgments, noting helpful conversations with Steve Strogatz, another major figure in this field.
Good to acknowledge collaborators and influences.
Section 6 provides the figure captions. Figure 1 shows the parameter space boundaries. Caddy and I say, etc., etc. Figure 2 illustrates the Hopf bifurcation scenarios depending on the signs of Pot and $3. Figure 3 compares frequency predictions. And Figure 4, as we said, summarizes the stable nonlinear states found.
Standard supporting material, the figures are crucial for visualizing the results.
And Section 7 is the references list. It includes foundational works by Winfrey, Kuramoto, Sakaguchi, the BNS and OK papers being discussed, plus key mathematical references on bifurcation theory like Golubitsky et al., and functional analysis like Reed and Simon.
The references place the work firmly within its scientific and mathematical context. #outro.
So we started this deep dive aiming to understand the onset of synchronization in large populations, tackling a seminal, highly technical paper by John David Crawford. We followed the unabridged protocol, meticulously moving from the basic Kuramoto equation through the Fokker-Planck description into the powerful machinery of linear stability analysis, O2, symmetry, and center manifold reduction.
And the journey led us to some crucial insights. First, the fundamental mathematical difference between this Kuramoto-Fokker-Planck system and Vlasov-type kinetic systems. The nonlinear coefficients determining stability remain well-behaved and finite here, even in the absence of noise. This makes the synchronization transition mathematically robust in a way that some other collective instabilities are not.
Second, the absolute necessity of respecting the underlying symmetries. The O2 circular symmetry, present when the frequency distribution is balanced, dictates that the Hopf bifurcation involves a degenerate multiplicity 2 complex eigenvalue.
Ignoring this degeneracy, as was done in some prior work, leads to incorrect predictions about the stability of the resulting wave patterns. Crawford's analysis, incorporating the full O2 structure, showed that for the bimodal population example, the Hopf bifurcation produces stable standing waves coexisting with unstable traveling waves. This resolved a key discrepancy in the literature.
We also saw the existence of the highly degenerate Takens-Bogdanov point, a complex mathematical crossroads where steady state and Hopf instabilities merge, hinting at even richer dynamics yet to be fully explored.
Right. It leaves us with a final provocative thought for you, the listener. We've seen that the stability and nature of these synchronized states depend critically on the details of the system, like the shape of the frequency distribution to omega and the proximity to degenerate points like Takens-Bogdanov. Coupled oscillators are everywhere. Think neurons firing the brain, Josephson junctions in superconducting circuits, flashing fireflies, even pedestrians on a bridge adjusting their stride. What real-world systems might be operating naturally poised near such a degenerate point, like that O2 Takens-Bogdanov point, where the very nature of their collective behavior, steady lock-in versus stable oscillation versus potential chaos, hangs in an incredibly delicate balance, sensitive to the smallest changing conditions.